So till now in the PCA, okay, can you please? So in the last week, the week one, we mostly dealt about the PCA, the standard PCA that we perform. Okay, so in the PCA, you already know what we were doing. We just have a data set, and then that data set can have some can lie on a linear subspace in the lower dimension. Okay, so that we were finding out, like with that from that larger dimension, we were just projecting those data set, or maybe you can just think of as PCA as just we were just finding some different bases, right? So and after finding those different bases, we were just projecting those data points, and then we were saving those standard, or you can say the dot, like the projection values we were like savings. Okay, and if we have to get back to the data set, we can get back to the data set if we just use all those eigenvalues, or you can say all those principal component if we are using, we can get back to the data set also. Okay, but mostly we like when generally we get back to some of the proxies, not the exact value but approximately those values itself. Okay, so the base, so the assumption that we were making in the PCA principal component analysis was maybe the data set can be in n dimension, but those data set can lie on a smaller, like lower dimension. Like let's for example, even though the data set is lying in 3 dimensional, that can lie on a straight line, right? That can be of R2. Or maybe if the data set is in D4, D5, but that can lie on a straight line or a simple plane. Okay, so that whenever those data set are lying on a lower subspace, okay, of a bigger dimension, we were just finding that what do you call that, that pattern we were finding with the help of the PCA. Okay, and if we are able to find the pattern, those were basically the direction that we were finding out, the maximum with the maximum variance or with the minimum reconstruction error. Okay, so that we were trying to do in the standard PCA, but there were some issue. So the issue from the assumption itself, the assumption what we are making, the principal component analysis, what does it help us? It was making some assumptions. So the first assumption that it was making, that maybe that whatever the data set on which we are working, that
It
can
should
that are lying on a lower subspace. Yeah, go ahead.
Yeah, it should like assumption like it is linear. The points, data points should be in linear subspace.
Yeah, correct. So this is the assumption that we are making, that if let's for example we are working on some data set, right? That's for example that has some isn't 3 dimensional, right? We were reducing it to some 1 dimensional or 2 dimensional. So what we were finding out, we were finding out one basis that is a combination of f1 f2 f3 itself, right? And that combination you can just think of as a, maybe this is in the 3 dimensional but lying in a straight line, right, nearby to a straight line, correct? And then we were projecting those data set on this line itself, but that line was lying on what, that was on a linear subspace itself, right? Even though the data set, let's for example, is in R4, but that can lie on what, that can lie on some let's for example just taking W1, and that combination of W1 can be a line, right? And then it can lie on the combination of W, let's for example W1 and W2, combination of W1 and W2, that will be what, that will be a plane, right? Similarly, plane we can visualize, but there can be some, if the data set is in R4, the subspace can be the combination of W1, W2 and W3, right? That is some flat line, but we don't know, like some flat hyperplane where those data set are lying. And if we are working on this data set that is in the R4, okay, and with the help of this data pore, we'll be able to find at least 3 principal component, right? Because we know that like we don't know, but okay, maybe this data set is lying on some linear subspace that is in the lower dimension, right? That is the lower dimensional of 3, like 3 dimensional. So we can have 3 principal component. Okay, and that 3 principal component can help us to know, like reconstruct those data also, or maybe to reduce the dimension, right? So from 4 to we are coming to the 3 dimension, maybe we can come to the 2 dimensional if this 4, the data set that was lying on a 4 dimensional was lying on a plane, like maybe the data set is 4 dimensional, okay, but that are lying on a plane. Are you getting, like everyone is getting this or not? Yeah. So so
Yes,
that
sir.
was our assumption that we were making. Yeah, correct. So this is the assumption that we're making while applying that PCA on any data set that was very huge data set. That huge data set, I mean the data set have a large dimension. Okay, that can have n number of dimension or d dimension, but we were transfer like changing that d dimensional to some smaller d dash, right? Where d dash was much smaller than D. This is what we were trying to do in a PCA, assuming that this the data set that was in the D dimensional maybe might be those data set are lying on a lower subspace of D dash. Okay, and that D dash principal component, that D dash can be a number, right? So D dash number of principal component, with the help of D dash principal component, we were trying to like maybe we were just trying to see the pattern. Okay, and if we are able to find the pattern with the help of D dash principal component, we'll be able to uh, tell like, or we were just storing, or with the help of that d dash principal component, it's like what d we're having number of d is like what, like standard, or you can say the canonical basis type of thing. It's not exactly, but you can just think of as d as the canonical basis, that number of canonical basis that were helping us to say about any of the data set, right? But now we came to d dash, that can be think of like we are just changing from d to d dash number of principal component also the same thing, like it is helping us to know about all of our data, right? But we are reducing from d to d dash, correct? So this is like now we are dealing with d dash number of principal component, or you can say the basis, right? And that is much smaller, because that was only working because that the data set that was in the d dimensional was lying on a d dash lower subspace. I hope this is making this is clear, right? At least this much is clear, right?
Yes, sir.
Correct. So this is our first assumption that we were making. Okay. But there can be an issue, right? There can be an issue. What will happen if the data point was not lying on some linear subspace, or maybe the data set that was lying earlier, it was lying on some nearby to some state. Maybe the x was belonging to RD, but it was lying on some straight line itself. Or maybe the x I was belonging to RD, but it was lying on some a flat plane. Okay, nearby to that flat plane. What happens if the data set are not lying in this circumstances? Maybe the data set can be lying like this, right, on a circle. The data set can be lying on a circle, right? So, or can be any pattern. It can be like this. The data set can be like this. So, if we'll apply PCA on this data set, this type of a data set, what will happen? Even though it was like, let's for example, we were working on a data set which were having only two features, okay, but the data set was not lying on some linear like you can think of as not lying on some line, because we just have two features, right? It was lying on some circle. Okay, if it was lying on a circle, if we would have done, if we would have applied the PCA, what will help? Just change the basis from F1 F2. Let's for example, it would have given this as a PC1, and this it would have given as a PC2. It just gives us a different basis with some constant. That constant that we apply is what? The variance would be maximum in that direction, or the reconstruction errors would be as minimum as possible. Okay, so it will help us to give this PC1 and PC2, because and you can't reduce it from F1 F2 to only PC1 or PC2, because you already know that the projection, if you'll just make the projection of this data point, this is the variance that you are getting in PC1, and this is the variance that you are getting in PC2. Okay, more or less both are same, right? You can't reduce one. If you'll just reduce one, you are losing almost 50% of the information, or the variance you are losing, correct? So you can't take PC1, or you can't take even PC2. I hope this is clear to you. Or let's for example, a data set is lying on some sinusoidal curve. This type of data set was lying like this. So here also it is difficult for you, right? So here why it is difficult? Here you are losing something else. You are losing the pattern. If you will just apply the PCA, you're just losing some pattern in the, so data set was lying on some different pattern. But now because you will just choose PC1, you are just losing some pattern, right? So you are losing something else also here. Okay, so PCA while, so this in this type of a data set will be, it will be very difficult for you to directly apply the PCA. Okay, so that's why there will be just learning about something else like kernel PCA. So as of now, So this is the first issue that we have incurred with. So the second issue what we have incurred with is, the second issue with the PCA is, see, PCA when we were working, PCA was simple. Like we were just, what we were doing, we were just maximizing something, maximizing the variance. Okay, so after doing those algebra and all, we were just coming up that we were having some, where we were having some argument, right? Like that we were just maximizing some function, right? And that function was something like this, right? Here we were applying some constant that the length of this should be one, because we were just worrying about the direction. We don't care about the length of the we are just worrying about the direction basically. Okay, so we were just finding that w where this argument function is getting maximized, right? W transpose CW, and then we came up with one solution that uh, the eigenvector corresponding to this, the eigenvector corresponding to the maximum eigenvalue of this covariance matrix. Okay, that will be the our best direction, or the direction with the maximum variance. Okay, and that see that we were representing what, 1 upon n summation of xi transpose. Okay, this is for our covariance matrix was, and that all the data set and whatever we are discussing, all those data set are centered. Okay, from the starting itself. If it's not, you'll have to do that. Okay, so this is our covariance matrix. So we were already knowing that for the covariance matrix, okay, we just have to calculate that covariance matrix, and then from that covariance matrix we just have to calculate the eigenvalues. Okay, but whenever you have a large set of dimension, the data set, let's for example the data set was in some d dimension, and that d is very large as compared to n. Okay, so let's for example that x that we were dealing with, that x was in very large dimension. Okay, that d can be of like, so you were, I told you about that one data set, right? MNIST data set. In that MNIST data set itself, it was very huge, like 784, I guess, that or maybe it was more than that. The dimension was. Okay, so that was even smaller, but if we'll just deal with some other pixel values with the image dataset and all, like the professor dealt about that, like it was consist of some 30,000, 40,000 of the dimension, right? So you incur with those type of a dataset where the dimension of those dataset will be very huge. Okay, and that is and that is like very huge, like the d dimension is like, d is very large. So when you will calculate this covariance matrix, you can just tell me. So covariance matrix, you already know that it is in the form of what? You can just write it in the form of XX transpose. So what will be the dimension of this XX transpose?
D cross D.
Correct. So it will be some d cross d, right? So you already know that this is what x is what x. I told you how do you represent x. So f1, f2, fd, and then you have xi till xn. Correct. So
D
this is in the
cross
form
N.
of d cross. Correct. So d cross n, and then you have n
N
cross d.
cross D. Yeah.
Correct. So the covariance matrix will be in the form of a d cross d, and we know that. So and this is like, and to calculate the eigen, so because we have to do that eigen value eigen vector decomposition. Okay, from there you'll be able to calculate the eigen values and the eigen vector, even though, and we have to calculate the eigen vector corresponding to the maximum eigen value. Okay, so that is going to take a like huge, like there is an issue of time complexity basically. Okay, because the dimension is very large, and to calculate the eigen values corresponding to, because you'll have to calculate those all the eigen values eigen vectors, right? So you'll have, because you have d, then you'll be having some d eigen vectors. Correct. That depends on the rank, but okay, let's, as of now, just deal with that. You'll be having d. So that will take a huge time. So what, from the, we just took the help of the linear algebra as, and here also we are just assuming something. We are assuming that you have that covariance matrix in the form of a d cross d. Okay, and that d is very large, and we are comparing d with what, n. So the number of, so you are just this, whatever we are dealing with, this will only work when the dimension is very large as compared to your number of observation or the number of data set that you have. So I was dealing with, so you just basically represent the data set in the form of what, you have some feature 1 f2. Okay, and then you have xi xn. Okay, so the all your column vectors are one data set for you. Okay, so each of the data set, each of the features will be represented like this. But here whatever we are incurring, so we incurred that the dimension of this data set is very huge, and that d is very very large as compared to the number of observation that you have. Okay, so what will happen, so if you have that d very very large as compared to the number of observation or the number of data set that you have, so with the help, so and we know some of the properties of, we have already learned about the linear algebra and we know some of the properties of the linear algebra, that one thing what we can do is, we where the covariance matrix for us is what, 1 upon n x of x transpose, correct, and this was in the dimension of some d cross d. So what we thought of, why can't we why can't we calculate the eigenvector or eigenvalues corresponding to x transpose x? Can somebody tell me what is the dimension of this x transpose x?
N cross N.
N cross N.
Yeah, n cross n. Okay, and I already told you our d, the dimension is very very large as compared to the number of observation or the number of data point that we have. Okay, so now we thought of, why can't we work on this x transpose x, as we have to calculate everything corresponding to the x transpose, right? And we were able, like we have to calculate the eigenvector, and then we thought that it is taking a huge time. So why can't we dealt with x transpose x? And from the linear algebra we know some of the basic properties, right? Both of them are symmetric matrices. Okay, and if you have x transpose and x transpose x, what are the features that we'll be getting, that what are the benefits if I just go and calculate eigenvalues and eigenvector corresponding to x transpose x? What will be the benefit that I'll be getting?
Both,
Multiple of ones.
Multiple of 1? No. So
can I say uh, both will have a same eigenvalue?
correct, both of them will be having the same non-zero eigenvalues, right?
Yeah,
Let's for
non-zero
example,
eigenvalues. Yes.
correct.
Yeah.
So if you have n very very less as compared to d, then you will be having some n only eigenvalues, and the remaining eigenvalues will be zero, right? Correct. And corresponding to that, you can get the vectors also. So we'll see that what are the relation between the if, because we have to get the eigenvalues, eigenvectors corresponding to this C matrix, right? So what will take help of this x transpose x, because this is in n cross n, and we know some of the properties of this uh, symmetric matrix, that is x transpose x. Okay, and there is some good relation between x transpose x and x transpose and x transpose x. Okay, and then we'll take help of those properties and we'll come up with some solution. Let's see that what we are going to do here. We know that if we have, because in the end we have to calculate the eigenvector or eigenvalues corresponding to x transpose. So let's for example if x, we are working on x transpose, because we know that n cross n is much smaller than d cross d. And if let's for example we are working on x transpose x, and let's eigenvector and eigenvalue corresponding to this matrix, that is n cross n. Let's for example lambda and v is the eigenvalues and eigenvector like pair for this matrix x transpose x. And if I have to, so what can I write? That equation, eigenvalue equation, I can write it here, right? X transpose x times let v is the eigenvector, so I can write it like this, like lambda times v. This I can write, right, from the eigenvalue like equation, right? You already know that a v equals to lambda v, right? This equation you already know about that. And this we just change, like for us x transpose x is the a, and okay, and this is eigenvalue, that equation that you write. Okay, v becomes the eigenvector and lambda becomes the eigenvalue. You're just doing some operation of a on vector v, and then that vector v generally doesn't change, like it just get magnified or maybe minimized, but it doesn't, the direction doesn't change. Okay, it got changed, magnified by lambda, so lambda becomes the eigenvalues and v is the eigenvector, okay, on which we are doing some operation. So this, if you'll just pre-multiply x, for example, if you'll just pre-multiply x, that we can do, right? We can do. So if we are just pre-multiplying, so what will happen? X transpose x v times x lambda v. Lambda we can just shift it anywhere because lambda is a scalar value. Okay, now what we can do is x transpose x v. what we have to get, we have to from here, because we were working on x n cross n, but we need what, we need the we need everything regarding the x transpose, right? Why do we take help of n cross n, like x transpose x? Because we know that the d is very large as compared to n, so that's why we took help of x transpose x. Okay, when we were doing this, we came upon one thing. Now we can write, can you get any idea from this equation?
We can write this like grouping it like x transpose equals
Correct.
xb,
Yeah, so this, yeah,
and this lambda
Lambda
we can take
XV.
outside, and lambda xb we can write.
correct. So lambda you can write it anywhere. So this equation becomes x of x transpose, right, of
Yes,
xb equals
right.
to lambda times xv. Can you write it
Right,
like this?
right, sir.
Correct. So now for us, now we are getting something, right? X transpose is our matrix for which we were trying to get. Okay, that is 1 upon n that we can do, but okay, as of now we have to dealt with x of transpose, right? So this becomes our like, now again if you'll see that this becomes our some vector v dash. This is lambda, and then again this same vector, right? So again if you'll just compare with this equation eigenvalue, that eigenvector eigenvalue, that equation that we write. So again this matrix we are just doing some operation x transpose on this matrix xv, then xv is getting magnified. Okay, doesn't change anything, just magnified with lambda. All right, so now we can see that we were started working on x transpose x, and the eigenpair was what, lambda, and v was the eigenpair, like eigenvalues eigenvector. Okay, but now we can see that x of x transpose has a eigenvalue, okay, same, but eigenvector is what, x times v. Correct.
Yes, sir.
So we got so now from here you would have gone an idea, right? So if we start with, and the dimension also you have be in mind that we are dealing with n cross n, and here we are dealing with d cross d. D cross d is very large, so that's why we are just taking the help of n cross n matrix. Okay, so I'll just recap again what we have started. Like, so we started with that some of the issue of the PCA, and the first issue that we incurred was the linearity. Okay, that if the data set is not linear, what will you? What we are going to do, that will dealt with that later. The second issue that we dealt with was, if the data set, because the dimension of the data set is very huge, what are we going to do? So now we came upon one idea. We just thought of, why can't we do the operation on x transpose x, that is n cross n, like that matrix is very small as compared to d cross d. So we worked on this. Okay, and from here, as if, let's for example, if lambda and v were the eigenpair corresponding to x transpose x, okay, that was n cross n matrix, why can't we take the help of that matrix? Okay, if we are able to calculate the eigenvector corresponding to x transpose x, that will help us to get the eigenvector corresponding to x transpose also. So why to calculate the like the eigenvector corresponding to x transpose? Because that is taking a huge time. Like, there was an issue of time complexity, because that was in the form of d cross d, right? So we can calculate the eigenvector corresponding to x transpose x, and then we'll just have to multiply this xv, right? And that will help us to get the eigenvector corresponding to x transpose, right? But there is one catch. We just have to normalize that vector also, right? Because we just worry about the direction, so we'll have to normalize the vector whatever we have got. So we got eigenvalues as a lambda and eigenvector as the x times v, and v is what, the eigenvector corresponding to x transpose x. I hope this much is clear to everyone, right? If you have any doubt, you can just ask me. I'll just wait for 1 minute or maybe 30 seconds.
So which one have higher time complexity, X transpose X or
X transpose. That's why we are taking help of x transpose x. So because we have starting, I told you, right, that d, the dimension of that vector, the dimension of the data point is very large. Okay, and that was very large as compared to that number of data points that we have. Okay, so that's why we took the help of x transpose x, because for the linear algebra we are getting some important stuffs, like if the eigenvector, if, because we can calculate the eigenvector corresponding to x transpose x, that is in the form of n cross n matrix. Correct, that is small, right, as compared to d cross d.
yes
So
sir.
just think. Correct, right?
So in this
Yeah.
case, the dimensions. the dimension of the data set refers to how many features we are considering for each data point, right?
Can you repeat that?
Sorry, what
The
I was
time.
saying, the
Hmm.
dimension of the data set
Hmm.
refers to how many features we are considering for each data point in the data
Correct,
set.
correct. Yeah. So
Okay,
whenever we are talking about the dimension, that's the features only. Yeah.
thank you.
Yeah. Hmm. Now, so if we'll just think of now, we got like we came from x transpose x to x transpose, and we got something right. Now we just have to make the whatever the eigenvector that we are getting. We just have to like because we worry about the direction, we'll have to normalize those vectors also, right? So if you have to normalize, what will be the value of this x times b? How can I write this matrix if you have to write b? How do you write this vector?
XB
XV
transpose
transpose XV.
into
Correct.
XB.
Yeah. So if I'll just write it like this, xb transpose xb. So if I'll just transposing this will be v transpose xv.
Mm.
Correct. Okay.
Yes, sir.
So we
Yes.
were knowing, yeah. So okay, from here, are you getting anything? X. We already know that for x transpose x matrix, what is the lambda eigenvalue is v, and corresponding to that eigenvector, sorry, eigenvector is v, eigenvalue is lambda, right? We already know that. We assume that, right? Lambda. Let's for example, lambda and v is the eigenvalue and eigenvector corresponding to x transpose x, right? So this is what, if you'll just see here, what can I write for this value? X transpose xv. This is what? This is just a
Lambda
matrix,
times
right?
B.
Correct. So we can write it like this: v transpose lambda times
B.
v. Correct. And this we can write it as what? Lambda v transpose v, because that is a scalar value. And this v transpose v, we have in the starting we have assumed that that is the eigenvector, right? Corresponding to v. So this value will be what? 1, right? So we are left with what? We are left with
Sir,
x. Yeah, yeah.
sir, how X transpose X is lambda?
X transpose x. Okay. So see, x, we have assumed that x transpose x is a matrix, right? And that matrix has
Yes.
lambda as eigenvalue, right? And if you have any matrix A has a eigenvector as v, you can write it like this, right?
Yes,
From
sir.
the so A is what for us? X transpose x, right? Times v equals to lambda v, correct? So this is what
Yes.
I just replaced it here. I can replace this, right? X transpose x times b equals to lambda v,
Okay.
right? Okay. So now what are the value that we are getting? X v ka whole square equals to what we are getting? Lambda, right? Correct. To x times v.
Sir,
If we'll just calculate the magnitude, that is what?
excuse me,
Root
sir.
of lambda.
Sir, sir, your X transpose B, how we got it one?
Where x, no, this is v transpose v. This is the eigenvector corresponding to this matrix x transpose x. Are you getting me?
Okay, sir.
Yeah. So now we can say that the magnitude of x times v is what? Root of lambda, right? So if that is root, and that you can just say like the prof has everywhere used, like I'll tell you what our prof has used. So and this, if you have the magnitude of xb as root of lambda, then now you can normalize, like you already know that if you have a vector something like that lambda times xv, then you can, what you can do is to get the unit vector, you can do it like this, right? So now for x transpose, you have eigenvector, sorry, eigenvalues and eigenvector also. And eigenvector is what? Eigenvector is simply some x times x upon root lambda times v, and that v is basically the eigenvector corresponding to your x transpose x. I hope this is making sense, right? Yeah, okay, that's it. So
Yes, sir.
yeah, so I'll just write it again, everything. So so we were having the issue first. Issue was regarding the dimension. So d cross d was taking a huge time because the covariance matrix C was upon 1 upon n x transpose. So this was in the form of D cross D. So what we thought is we should do for X transpose X. X transpose X as n cross n matrix. There is a n cross n matrix, and the time it will take much lesser time to calculate or do that eigen value decomposition. Okay, so we just assume that if X transpose X has a lambda n v as eigenvector and eigenvalue or the eigenpair. Okay, and from here we just came up to X transpose where we got the eigenvalue as same eigen vector as same eigenvalue as lambda, and the eigenvector we got it as xb times root of lambda. Okay, this is clear to everyone. So the first issue that we were having, where the dimension was very high as compared to the number of observation or the number of data points. Okay, so now what we did is, because we have to calculate the eigenvector or the eigen vector corresponding to the maximum eigenvalue for x transpose, that is the covariance matrix, like 1 upon x transpose, that is fine. So we have to calculate the eigenvalue or the eigenvector corresponding to x transpose, that is our covariance matrix. Okay, so we took the help of x transpose x. I hope this is clear to everyone, right? Is it clear to everyone? Okay. So now we have almost dealt with the first issue that we were having. So the same thing has been dealt in a different way by our prof, but that's fine. Like both the things are same. There it's just that he just explained, like elaborated all the steps. Like we just took the help of the linear algebra, and then we came upon the final result that the covariance matrix corresponding to the x transpose will be we can take the help of the x transpose x, and then we'll get back to that, right?
Sir, for your this last statement, sir,
Yeah.
x
Which one?
x transpose, it is a pair of lambda comma xb upon root lambda.
Huh?
How is it seen?
How?
This xb upon root lambda.
How did it came?
Yes, sir. Yes.
Okay, so yeah, we saw that here, right? So we saw that, like, if we were having x transpose as a matrix with eigenpair lambda and v, then x transpose also will be having the same form of a lambda. The lambda will be always same because both are symmetric matrix. And if we have, let's for example, this was having the rank of the matrix was r, then the rank of the matrix for this matrix also, the rank for this matrix also will be r. So you'll be getting some r number of lambdas, right? Okay, non-zeros lambdas. Okay, so the lambda will be same, and then we came upon one conclusion that the eigenvector corresponding to this matrix xx transpose was xv, and then what we had done is we have just normalized that. When we have normalized, we just the normalized eigenvector, we got it like this we got it from here, that if we just, because here what we did is the length, like we just if you have to normalize any vectors, what will you do? You'll just divide it with its magnitude, right? And so this is what we have done. We have just calculated the magnitude of xb, and then we have divided it with that, so we got the unit vector. I hope this is clear. So this is our eigenvector corresponding to xx transpose. This is what I have written. Okay, is this clear now, Sudhir, right?
Yes, sir. But I do not get how above statement is written, sir. xb in this form. How this eigenpair we are getting for the x transpose lambda and xb in above, how it is converted, sir?
So
From
lambda is a
x transpose x, we have taken it as lambda and v as eigenpairs.
yeah.
Then how for x transpose, how it is converted to lambda and lambda v upon root
X.
lambda?
So this part is clear. How we came upon from lambda v to lambda xv. This part is clear.
Yes, sir. That is clear.
Okay. So just asking. So okay. So now the next part is, we for any vector, how do you make it as a unit vector? How do you orthonormalize? Like, do something like you divide it with its magnitude, right, to make it as a unit direction in a unit, like unit vector, right? This is what you do.
Yes, sir.
Correct. So now we just came upon, we have to calculate, because we were getting this as eigenvector, we have to divide it with the magnitude, right? And then we saw that xv, because this is how you do, right? If you have to calculate the magnitude, how do you do? For any vector, you do it right, v transpose v, right? For any vector, that is in the form of, if you have to write v square, just write it like this, right? V transpose v is v square, correct? So for this vector xv k square, we can write it like this, we can write it like this. This you can just assume that a square equals to a transpose a. We just did the same thing, xv
Okay,
ka
okay.
transpose.
Got
Got
it, sir. This lambda is
got
the
it.
value of norm xv. Right.
Huh, correct.
Okay. Thank you.
And the same thing, if you will just take, if you'll just start with, you will just consider that 1 upon c x transpose x, right? If you'll just start with this and then consider for this lambda and v, then for this x transpose x, the lambda will become n lambda, correct? And then you're left with what? N lambda, and this will become root of xb upon under root of n lambda. See, if you'll just start with, you'll just consider that 1 upon x transpose x का eigenpair is lambda and v. Then for x transpose x, what will be the eigenvalue? N lambda, right? Correct?
It is lambda by n, sir. It will be
No, no. So this is c, and if you have to calculate for cn, this becomes cn, right?
right, right,
C
right,
times n. So now the eigenvector will become n times lambda, right? And now
right.
you have to calculate it for x of x transpose. X of x transpose, if you have to calculate, I told you, right, what will become? N lambda times xv upon root of that lambda that you're getting. The lambda was what? N lambda. So it will become n lambda, correct? So this is how our prof was dealing. I hope this is making sense to everyone, right?
Clear, sir.
Clear, right? Clear to, I guess, everyone. So in the lecture also, the same thing has been dealt with, but in a different way. And then in the end, you come upon the same conclusion, that you have some eigenvector, you start with x transpose x, and then you calculate the, because the dimension was very high, so you dealt with x transpose x matrix because it was n cross n. And then we came upon some final conclusion that this will become the eigenvector corresponding to that eigenvalue. Okay, so I'll just write what are the, like, if you just dealt with those issues where the dimension will be high, you don't, like, it's very simple. You just compute what k. Generally, it has been represented in the form of a k x transpose x, right? Because this will be in n cross n, that is much smaller as compared to your d cross d. Okay, compute the, do the eigen decomposition, that will take much lesser as compared to the other one, because here the dimension, here it will take much lesser time because it is in the form of n cross n. So it's much easier to calculate that. If for this matrix we have, I'll just use the same thing that our prof was using. So beta he was using. So beta times, let's for example, the rank for this matrix was k. So you'll be having n n lambda to n of lambda k. I hope the same thing he was using. Okay, so this is our eigenvector and the eigenvalue corresponding to the n cross n matrix. And then in the end, you already know that because we have to get it for x of x transpose, so it will be in the form of some, he was using some alpha, and alpha was what? Or the, I can write it the vector itself. The vector, the eigenvector corresponding to x transpose will be in the form of some x times this beta upon root of n lambda. Correct? I hope this is clear. Any doubt that you have, you can just ask me. Anything that you have.
No, sir. Till now it's clear.
So till now it's clear. Whenever you are, if you are dealing with problem where the dimension is very high. See, if the dimension and the number of observations both are almost comparable, right? Then you can't do much, because both are comparable, both are very large. Then you can't do much. Right? So you'll have to use that standard PCA, even though There are other methods, but if you just want to use the PCA, you can do that.
Sir, here beta k is eigenvector.
What?
Beta k is the eigenvector.
Corresponding to your starting wala matrix, starting that X transpose X.
Yes.
Yeah.
Okay.
So
So,
what do you do? So because you have X transpose is very high, so you start with X transpose X. You calculate the eigenvalue corresponding to that, right? Because you have, and what you'll do, because this is n cross n, smaller matrix as compared to your D, because we are assuming that D is very large, right? So you calculate the eigenvector, and then with that eigenvector, you can come upon the eigenvector corresponding to X transpose also, right? This is what we were discussing from the starting, right? Yeah. Anybody else? Any question? Was asking something?
sir, we need to first centralize the data and then apply this algorithm. No?
We have to.
First centralize the data.
Yeah. Everything is been done after centralizing the data itself,
Okay.
because the covariance matrix, the value that itself will change, because you already knew the covariance matrix is what one upon n summation of x minus mu, right? Upon transpose x minus mu. So if you are not centering the data, the covariance matrix itself will change. So you have to do that centering in the starting itself. That or feature, that what do you call normalization, so that the feature value, each of the feature value, the mean will become 0 and the standard deviation sigma square will become 1. That you do during the pre-processing of the data itself. Clear?
Yes, sir.
Okay.
Clear.
Okay. So we dealt with the first problem that we were facing in the PCA. So we were having some issue regarding the dimension, so we fixed that issue, right? And now we have the same thing. So you can just keep some n PCA or whatever the number of PCA that you want to keep it. You can just keep those many PCA, okay, the principal component, and then with the help of that, you already, after that you already know that how do you do the standard PCA. Like you have to just keep 95% of the information. That's the thumb rule, but even though you can just change it, that depends on you, but mostly you just have to keep 95% of the information, and depending on that you can just keep that many principal component. Okay. One second. And after that you can just keep whatever number that you want to keep the principal component as. So okay, and okay, I'm asking something like from the starting week, the first week itself. If you have to do the full reconstruction of the data set, how can you do that full reconstruction?
By taking all the eigenvectors.
Yeah, by taking all the eigenvectors, right? So you already know that if you have to, if the data set was something RD, and you have taken, let's for example, that was in some k dimensional subspace, right? So you will be taking how many? Okay, so your data set will become what? The reconstruction data set will become what? Xi transpose Wi times Wi Xi transpose Wk times Wk. This is your reconstructed data set, and if you want to get the exact data set, that you can use all the principal component that you have. Okay,
I mean,
from
till
here can you get
W,
the, yeah.
if we, I mean, if we want to do the XI, I mean, here the reconstructed XI we are doing. If we want
Yeah,
to do XI only we want to get, then we have to do till WD. I mean, all
correct,
that.
so this is the reconstructed wala, and if you want the whole, like the exact reconstructed Xi, like this will be almost equal but will not be
Yeah,
exact same value.
exact.
Yeah, it
Yeah,
will be approximate.
correct. Yes, sir.
Yeah, but from here you'll get the exact value. Xi transpose W1 times W1 Xi
Till
transpose WD.
WT. Right.
Okay. Because you already know that what is the formula of the reconstruction? Xi minus XIR. Right.
Correct, sir.
That will become 0. But when you're just taking Xi and XIR both as the same. Okay. One more thing, and that will help you in the kernel PCA also. Whenever you were representing with the help of the you were what you were doing, you were just going in from the some bigger dimension to the smaller dimension where you were just taking the help of some PCA, some different basis, and then with the help of that different basis, yeah, Rabi, you were asking something.
Sir, can you scroll a bit up?
Yeah,
Yeah, XI, yeah, uh, there is the formula just above the formula reconstruction formula. Just above the
yeah, this
reconstruction.
is the data set. Like if we have a data set like this in the form of E1 E2, right, different one basis, right, this basis you can just 1 0 and 0 1. How do you write any data point? If the data point is here, how do you write? If xy is there, you write it like this, like the projection x is the projection here and y is the projection here, so you write it like ex into e1 plus y times e2. This is how you write, right, xy. Similarly, for if you have just changed the dimension from this is becomes your pc1 and this becomes your pc2, then how will you'll just calculate the projection of this data point on this pc1. So this will become what? The projection of this data point xi times pc1 multiplication with pc1 plus xi transpose pc2 times pc2. Correct? This is your data point, right? This is how you write the data point. The same thing I have done here, because I have now that many wk time, like wk dimensions I have, the basis I have, right? So I can write this xir in this form, right? But if you have to write the same data point, I'll just take the help of all the principal component that I was having from wi to wd. So then I'll get the exact data point.
Sir,
Is it
what is
making
R
sense?
in that, sir? What is R in that?
This are you're talking about.
Yes, sir.
This is the like the reconstructed with the help of k principal component, the k based principal component.
Okay, that is symbol for reconstructed.
Yeah, yeah. And this is the
Okay.
exact data point that we have got here because we
Okay,
have
sir.
taken the help of all the principal component, right? But one more thing I want to know, like when you were just you have done the principal component analysis, so with the help of that you were just your principal component was some of the representative, right, for your data set, right? So after that you were transforming your data set, right? And that while transforming your data set, what you were storing, some scalar value your project, like some scalar projection you were storing, right? What was that? So if you are just coming from, let's say, and that will help you in the kernel PCA also. In the end, you'll come upon one concept that if, let's for example, you're coming from RD to some RK, okay, XI, your XI belongs to RD itself. So your transformed data set, because you were having, let's for example, this is PC1 till PCK. This corresponding to xi, this is corresponding to x2, similarly, sorry, x1, and then xn. So you were storing something, right? What you were storing here for each of the data points, something you were storing, right? And this is the final, like the transformed features, right? For now, what was those values? Can somebody tell me?
Scalar projections only.
Yeah, that is what the projection value,
X.
right?
Right.
Xi transpose, x1 transpose, PC1. Similarly, for this data, if the same data point, if projected on the kth, then xi transpose of pck. Similarly for x2, x3, for all the data points.
So
Correct.
I
So
have a
in the
doubt.
end, you get, yeah, yeah.
So we started with X transpose X, which was a n cross n. So we had n eigenvectors. So
Huh.
my doubt is that in once we converted to X transpose, so then how does the like dimension change accordingly? Like from n cross n to we again go back to d cross d.
Okay. See, that's like linear algebra. See, if you are computing anything in the form of x transpose x, right?
Yeah.
And in the end, what is your vector? What is the dimension of this x? So I
This
guess you're asking. So this for the eigen, you're asking. I guess the beta. What is the dimension of beta? Beta is what eigenvector, right?
yeah. Yeah.
What will be the dimension for this beta?
This will be n cross n. I mean,
No, that's a one column vector, right?
one column vector.
Then what will be the dimension? N
Uh,
cross n cross one, right?
n cross one, right?
It's like a column vector, right? So column vector, so okay. Now we have calculated for x transpose, right? What will be the dimension of W? So what is the dimension of x?
X is d cross n, and that is d is n cross one. So d,
Yeah, the n cross one.
d
So
cross
left
one.
with what? D cross one. It should have came, right? So D cross one you are getting for each eigenvector, right?
Right. Okay.
Yeah.
Okay. Thank you.
Yeah. So what I was saying about any other doubt anybody has regarding the dimension or anything? If you have any confusion, no, right? Okay. So you were storing in the end. You were storing the projected value, right? So if you have just keeping k principal component, you are just storing the projected value for each of the data point. You just projected on the PC1, PC till PCK, and you were storing those values itself, right? At the end, you don't have to worry about the eigenvector. It's just that you just storing this value, and on this value, on this data, the transform data set, you are working. Correct? Yeah. So this concept will help us later. Now we'll come upon the second issue that we see. The second issue that we are facing is the issue 2 that I told you in the starting also. Our assumption, the basic assumption of PCA is what? The basic assumption is the data set should lie on a like some linear subspace, the low like or maybe in the some lower dimensional subspace, right? So let's for example, if a data point is lying something like that, I told you one example. If lying in a circle, so what are the options that we have? We can't directly use the standard PCA, right? Why can't we use? Because if you'll just you want to take this or this, anything if you'll take, you're just you can't decrease the dimension. If you'll just go from 2 to 1, you'll just if you just want to keep this dimension PC1 and this is PC2, if you're just applying the standard PCA, then if you want to keep this direction, it will not be helpful for you because you are just losing almost 50%, even more than 50% of the variance or the information, right? The spreadness you are missing. Even though if you just keep PC2, there also you are just losing some 50% of the information. So what else you can do? What can we do here?
We
If we
will
have gone,
increase dimension.
we will do.
We will increase dimension.
Okay, so how are you going to increase the dimension?
Suppose that
More kernel.
What will I do?
it's this is a linear data.
Yeah.
I mean, if there is relation in x and y or axis. Then we will increase one dimension that is in z. By that we can form any relation.
Okay. Anyone else? Yeah, we will. That's correct. Like basically, you're just increasing the dimension. But why we are increasing the dimension? Why are you going like? Why do you want
For
to go to the X Y Z? Yeah.
finding the relations.
What will you do?
For finding the relation
With
that
like?
what we
Sir, so
can.
that the relation between the all the points is linear, not quadratic or something. To
So
make
like
it linear, that's why.
when you have a term of like a higher degree, like if you have quadratic, then you have like if you make the relation into its multiple terms like x squared to x and like that, then it becomes linear. So like you map it to a higher dimension where like with the separate terms of the function it becomes.
Yeah, correct. So basically, what we are trying to, because we are always comfortable when the data set, maybe the data set can be in some bigger dimension, but we are comfortable working with the PCA on those circumstances only when the data set lie on some linear subspace, like small or maybe some lower dimensions. Like if you are working on some 4-dimensional, 5-dimensional, if the data set is lying on some two-dimensional plane or one-dimensional line itself, maybe the data set can be in 4-dimensional, 5-dimensional, but the data set lie on some simple dimensions, or maybe simple straight line or some flat plane or flat hyperplane. Okay, if those data set are lying there, then it becomes very simple for the PCA, for the algorithm, to work on that and then find the pattern, find those patterns. Correct. Maybe the data set can be in n dimension. So if the data set, let's for example, I was giving the same example, maybe the data set lying on belongs to RD, but the data set was in some bigger dimensional D, but actually those are lying on some flat plane itself, that is of 2-dimensional, right? So if those data set are lying on the flat plane itself, then it becomes very simple for the principal component analysis, like this algorithm, to find this pattern. Okay, and then finding this pattern directly, it can come from the d-dimensional to the 2-dimensional, directly from d to 2-dimensional. Okay, it will find some two principal component, because with the help of 2 dimension, okay, we can just represent all those data points lying on this plane, right? So that is what like our algorithm help us to do, right? If the data set, even though it was lying on the d-dimensional, if it was lying close by to some straight line itself, then with the help of only one representative, we were able to reconstruct or maybe find a proxy corresponding to those data point, because that was lying nearby to that line itself. Maybe that is in d-dimensional, but actually those are lying on some straight line itself, right? That straight line can be one representative, right? That can be a combination of those features, and that is in some simple, with the help of only one principal component, I am able to define those data set, right? Or I am able to find a representative for all those data points, right? So here also what we are trying to do is, because we are not able to, principal component is not able to find any pattern here. So what we can do is, we can just try to increase the dimension for this data set. And how can we increase the dimension? We'll just try to go in some, like whatever the data set, like for example, for each of the data set f1, f2, f3, like f1, f2, all the, for each of the data point we have some f1 and f2, right? What we will do is, we'll just do f1 square, and that can be our new features. Okay, let's for example, this is capital f1 and capital f2 is our second feature. And then let's for example, after doing this, okay, we have just increased the, and maybe we can do something else also, making f1, f2 or something we can do. And then after doing that, we just came upon one thing, that after doing this, the data set becomes very simple. Or maybe it was on the f1 and f2 now, but the data set becomes very linear. Or maybe it was lying on the 2-dimensional, but with the help of one representative, I am able to extract all those data points, right? Maybe this data point, all those data points, after doing this f1 square and f2 square, this becomes in this, like this was close by to a line itself. And with the help of one representative, now I can extract the data point, or I can represent those data point with the help of one representative. Correct. So what have we done? We have just squared. So whatever the features I was having, I just did the square of that, and then I thought of f1 as a new feature. So we have done some mapping. It's like a function, we have some apply some side of a psi function we have applied on each of the data points. And after applying some psi features, okay, that after applying that features or the mapping, that becomes our new, like the whole data set matrix. So in the starting we were having some matrix, right? And that was f1, f2, and the data set was there, xi to xn. Now what I did is, I just did f1 square, f2 square for each of the data points. Now I have a different matrix altogether, right? The data set altogether, the data matrix you can say altogether, right? And now I, after that I have applied a PCA on this new data matrix, and after applying those new piece, like the principal component or PCA on this new data matrix, we came upon one fact that with the help of only one PCA, I'm able to represent those data points. So now you got an idea, right? So maybe there can be a possibility that your data set is not lying on some linear substrate, or maybe some simple pattern, some flat pattern. Okay, so what we can do is, we can go to some different dimension. Okay, and in that different dimension, we can try to get some linear or linear subspace, right? And if I'm able to get some flat pattern or something very simple where our PCA can work, okay, if I'm able to map those data points in some different dimension, the data matrix can be totally different from whatever we were having in the starting, okay. But if I am working on that new data matrix and I'm able to work on that, and if I'm able to get some principal component from there, so from there we can reduce the dimension, right? And then at least what's our main goal? To find some pattern, right? And if I'm able to find some pattern, after that I can work on that data matrix, that updated data matrix, and then I can do whatever I want to do. Maybe I can do the clustering. Maybe I was about to do the clustering, but here the data set was not in that pattern. I was not able to find some pattern. So what I can do is I can go in some different dimension, and in that dimension, after going in that dimension, I can see that there is a pattern of. So after that, I can find some pattern. I can work on that data set, right? I can do classification, regression, whatever I want to do. Even I can work. I can do the PCA also there, right? I hope the idea behind this is clear. The kernel, or not the kernel as of now, but at least this idea that if you don't have the, if the features are whatever the data set that you have is not in some simple linear subspace, or some simple pattern, then you can do this also. You can just do some mapping, some transformation from this dimension to some different dimension. That can be very high also. That's not an issue as of now. So we can go to some different dimension also. And if I am able to find some nice pattern there, because in the end we have to find some pattern so that our ML model can work. Okay, any ML model, not even not only the PCA, any model uh, mostly can work if we are able to find some pattern, because you don't have any label as of now. I hope this is making sense to you. Okay. Okay. So now what we'll do is, but here also there are some problems here also. So we were having some, because the data set we were have to do the feature transformation, right? Because this is the feature transformation itself, right? We are just transforming our features from some one dimension to some bigger dimension, right? And while transforming this feature, see what happens is, it that also is a very tedious. Say, let's for example, you have a data set, right? You have xn data set with some feature, okay, f d. If you have to transform, if you have to apply some mapping, because your data set, the PCA is not working fine on your data set, right? You're not able to reduce the dimension. You're not like you're not able to find your PCA doesn't is not able to find the pattern. So you can do the transformation. But the problem here is, if you'll just do the transformation like with the help of some mapping, that also is a very tedious job. How can you, like, you can do that, that's fine, but that again it's going to take a lot of time, right? Because if you'll just do each of the data point, you will transform, right? Because here itself we can see that we were just doing for the two features. We'll have to do square, and then again, like, the same, like we'll having some issues to transform each of the data point, right? So here also you can't do that. Like, you can do that, but it is going to take a lot of time to transform those data sets. And the problem here is, we don't know, like, after transforming also, whether we'll be able to get some good pattern or not. So it's a very hit and trial method. We'll be doing some mapping and then finding, doing mapping and then finding. So that becomes very tedious job to do that, right? So what we came upon is, like, we came upon some functions that was a nice function that helped us. And why it helped us, that also there's a reason. Because, see, what happens if, let's for example, this is our function that you have. So this is, you have done some mapping, and then after doing the mapping, you got some phi matrix, right? After doing the all your transformation, you got some, you have applied this mapping phi of, that can be anything, maybe the one that we have seen, that square of that term, right? So that can be one of the mapping, right? and that mapping, after doing that mapping, we got some matrix like 5 1 5x 1 5 xn, right? We got something. But as we know that like this is going to take a lot of time to do that, right? So see, one second. Yeah. So yeah, we were dealing with the features. Yeah. So what happens whenever you have to transform those data point, and the problem with this is you don't know even after transforming whatever the transformation that you are applying, you'll be able to get a good, like the good feature that you are searching for. Whether the PCA will be able to find some pattern or not, that also you don't know. So it's a very hit and trial method, and it is very going to very be difficult to do that, right? So what happens is we just came upon some of the uh, good functions. Let's for example, so basically we deal with, in the kernel PCA we deal with two of the important function. One is the polynomial with some degree, and then one is the Gaussian function generally. Okay, so what happens, you will just deal with some of the kernel function. So we have to just discuss about the polynomial with the degree p. But even though we'll just discuss a bit about the Gaussian also. So the first function that we came upon was the kernel function, and that kernel was a polynomial kernel function. So yeah, if every so anybody has, if went through the lectures, why are you going to, why we are going to use the kernel, the polynomial kernel function? Can somebody tell me?
Because
The
we can do
dot
a
product
transformation.
works in higher dimensions.
Yeah, that's fine.
It will
Yeah.
directly give us the dot product, I guess.
What?
It will directly give us the dot product instead of finding the answer through the function. It will directly give the dot product.
Correct. Yeah. So that's the correct answer, because yeah, because we are, I told you, right, it's very difficult to transform, do the mapping, and then after doing the mapping we'll have to work. So it's better in the end, I told you that in at the end of the day, whenever we were calculating for the covariance matrix that was in the form of 1 upon n xx transpose, what was this value xx transpose? If we'll write in the form of the matrix, what are you getting? You are multiplying this x and x transpose, right? So how do you multiply, how do you do the matrix multiplication? What will be the like for example, if c of ijth term, what will be the value of c of ijth term? Can somebody tell me what will be the value of C ith term? If you are multiplying something, any two matrices, that is 1, 2, and 3, 4, and here you are writing 1, 2, 3, 4. What is the first term that you are getting? The first term here. What will be the value you are getting? We are just doing the column and the row
Yes, sir.
multiplication, right? The
Hmm.
column of the first matrix and the row of the second matrix, correct? Correct. So that basically is what you are just multiplying one. If you'll just write the correct, so xi transpose, if you're just writing in the form of a xi, so this basically is what xi transpose xi, something like that, right? So that basically, so in the end what you are doing, so you are basically, you have all the values of the dot product, right? The similarity between ith and the jth vector, correct? That is what you have for all the matrix that you were, so for the matrix for which you were calculating the eigen vectors or the eigen values, that was what, that was simply the dot product, like each of the values in that matrix was a dot product of some two vectors, right? So what we are doing is, because it was very difficult for us to get the phi and all, right? So the mapping, even though you can get it, but it is difficult. So we just use that concept. The concept was what, the dot. So the covariance matrix that we were getting, that we have to get in the standard PCA that we are working. Okay, that in that standard PCA, you were working with that covariance matrix, and that covariance matrix for each of the values that you have thoroughly checked it, and that was basically the dot product of some two vectors, right? That you were working on. If it is I jth value, then I column and jth row. Okay, that is how you're working on, right? So here also, because kernel function can help us in getting the direct if you are just in the kernel function, what happens is basically I'll just tell you how does you represent that kernel matrix, okay, or the kernel function. You represent it is like if you're just giving some x and y or maybe x transpose. You can just write any constant also here. There's no problem in that. So see when, and let's for example we in the lectures also our prof has just discussed about where the degree, we have just discussed about the polynomial with the degree 2, right? And then we when we expand this that polynomial, we came upon one thing, that whenever we were expanding, it was coming up in the form of some dot product. So that becomes helpful for us, because at the end we just some matrix that will be in the form of some, that will be in the form of some dot product itself. If here if you have to write k of I, that means the similarity between two vectors, right? Similarly here if you are just writing k of 1 2, then that also is the similarity between two vectors. Similarly for all the values which are available in your matrix, right, the transform matrix that you have came upon, right? So that also consists of or not the transform matrix, basically the covariance matrix of the transform matrix, right? That is in the form of some uh, that is in the form of some similarity between two like the transform matrices, right? So this can be in the form of what, if you will just write it, k of I 2 cross 2 any matrices, that will be in the form of phi of xi transpose phi of xi. Similarly here it will be, so you can just write it in this form, right? Correct? Is this clear to you? So why we are using the polynomial function? Okay, I'll try to make it. See what happens. So in the starting when we were dealing with the covariance matrix, so I'll just repeat it again. So we were dealing with the covariance matrix that was in the form of 1 upon n x transpose, right? And when you will do the multiplication, that is what this matrix is, what xi multiplication of some different matrix that is in the form of x transpose, right? Correct? Are you there? Are you able to hear?
Yes, sir.
Yeah.
Yes, sir.
Okay.
Yeah.
Yeah. So what I was trying to say is, because mostly the covariance matrix for which you have to calculate the eigenvector or the eigenvalue, that was somewhat the common the dot product of your some two vectors that you were dealing with, right? Because you have some n vectors and n data points. Okay, so you have to calculate the covariance matrix, right? And you were dealing with some x transpose x or xx transpose anywhere. When you were doing the product of those, the covariance matrix that you were getting, right? Maybe it can be in the form of x transpose x or xx transpose. That was what, that was basically for each of the element that you were having, each element was some similarity between two vectors. That's basically the dot product. Dot product tells you about the similarity between two vectors, right? And that is what you were calculating. So we, it just strikes us that it, we don't need for the covariance matrix for which we have to calculate the eigenvector or the eigenvalue, we don't need exactly the each and every element or the each and every data point. We just need the dot product of that, right? So what we have done is we just started searching for that type of a function that can give us this type of a matrix where we'll just put the vectors and it will help us to get the values in a different dimension and in the form of a dot product. Okay, so we came upon with a one function that is the polynomial of degree p, and that function was in the form of xi. If we are just putting xi data point and jth data point, it will give us this type of some function. Okay, and that function, that depends, like if you want to go in some bigger dimension, very high dimension, that you can just increase the value of a p. Okay, and you just have to put xi and xj, it will help you to give some values, some output values, and that will be the dot product of some. So this is similar to, let's for example we can just do for one value. the same thing that our prof has discussed. Let's, for example, you have a function, have a data point f1 and f2, and you have a one data point x dash or xi is this one, and xj is g1 and g2. And you are dealing with the polynomial transformation. You just are doing the polynomial transformation of two features of degree 2. So here we'll be taking p equals to 2, right? So the function, our polynomial function is just for trial that whether this function generally are giving us the dot product or we are just taking normally. So if, let's for example, it was what, 1 plus xi xj to the power whole square, correct? So we can do it like the x transpose. So if we'll just take it 1 plus, one vector is what, f1 f2, the other is g1 g2 to the square. So what will we get? 1 plus f1 g1 plus f2 g2 ka whole square, right? So here we'll be getting something, right? We can get f1 square g1 square plus f2 square g2 square, and that will be 1 as a constant. 1 plus, then you can have 2 times this f1 g1 plus 2 times f2 g2, and then you can have 2 times f1 g1 f2 g2, correct? So what is the dimension of this? So what will help, how it will help us? See, you can just write it in the form of a dot product also. How can you write it? You can just think of f1 and g1 square. So you can write it as f1 square, here g1 square. Similarly, you can write it as f2 square, g2 square. Okay, and then the third 1 you can write it here, 1 g1 square, that is fine. And then for this you can just take it as root of 2 f1, here you can write it as root of 2 g1. Similarly, here you can write it as what, root of 2 f2, and here also you can write it as root of 2 g2, and the other you can write it as root of 2 f1 f2, and here also root of 2 g1 g2. See, this is what, this you can think of as one transformation, right? And this is what the other transformation. Are you there? See, this you can just think of as one transformation, and this is for the other transformation, xi and xj. See, if you would have done the transformation, this type of a transformation where you were having the starting, you were having only two features, but you have done what? You have done some of the transformation, and then from the d equals to 2 dimension, you just went to d equals to some 6 dimension, correct?
Yes, sir.
Yeah, correct,
Yeah.
correct.
Correct. So from here d equals to 2, you just went to some 6 dimension, and after that you were just trying to do something also. So you were just doing, so 1 to, you have just taken the constant, then you have done for f1, you were having, you have done the f1 square. Similarly, you have done f2 square, and the third one feature that you have taken is root 2. Maybe the constant can be anything, but f1 you have taken, the other one you have taken f2, and then the other one you have taken f1 f2, correct? So you are going in the, you are using basically what you have done. Even though you would have taken the function itself, the mapping of this mapping, you can take it directly also, but it was very difficult for you. Like, you can do that, you can just do the hit and trial, but here also we are doing the same thing. We are just changing the value of the p. With the changing of value of the p, we can get the hell, like n number of different, like we can directly go from some d to some d dimension, and that d will depend, like the formula, there is a formula that it will go to what, p plus d c 2 I, what is that? So it will be what, if you can check it, so this is what, 2 plus 2 c2, so that is 4c2, that is 6, right? So it is going to some 6 dimension, right? So here also you can see that we are going to some 6 dimension, correct? If you are just taking the help of this polynomial transformation of degree 2, you are directly going to the some 6 dimension, even though you can use that mapping directly. But here what happens is, because we were just for the in the matrix we were just using the fact that it is just taking the similarity between some two vectors. We are just, so here also in this polynomial transformation function also we just give two different function, right? Two different function, I mean two different data set, and then it will give you the similarity between those two, and that you can put it in the matrix, right? Similarly, you can just give it whatever the number of values that you have, whatever the number of data set that the data point that you have, it will help us to give you some matrix, right? Because for each of the data point, each of the two data point that will give you, that you'll put inside the polynomial function, it will give you some value, right? And that can help you to construct a data matrix, an upgraded data matrix from some two dimensions to some bigger dimension, correct? And then from that bigger dimension you can help take the help of the standard PCA and then work there. Are you getting me or not?
Yes, sir.
Yes,
Yeah,
sir.
yeah.
Yeah.
So have you got the what was the issue and how we are trying to solve that? Yeah,
Yes, sir.
so our first problem was the number of dimension. The number of dimension was very high, so we try to reduce that with the help of the other, like we use the help of the X transpose X matrix, right? And from the help of the linear algebra we came upon some conclusion, and that conclusion we already did. Now the next problem with us was the whether if the data point is not lying in a linear subspace, the smaller subspace where the PCA can work, because the PCA generally PCA will work because it assumes something. It assumes that the data set is lying on some lower subspace, right? In some flat pattern, okay, some simple pattern where it can find the pattern, right? But if the data set is lying on some like, for example, we were taking the help of some that the data point was lying on some circle. Okay, so there it was very difficult for the PCA to work because it will not work. How can it work? Because the PCA directly tells you that my assumption it is like the data set would lie on some simple should lie on some simple pattern, some simple linear subspace, right? If the data set is lying not lying, I can't work. It will give you some bad, like it will work, but it will not be. You'll be losing a lot of information if you're just taking some out of if you are reducing the features, right? So for those cases, what we are trying to do is we try to map those features small dimension to some bigger dimension, and then in that bigger dimension we'll try to find some pattern. So while doing that, what we are doing is we try to find some mapping, okay? Because mapping, so we can find that, but that will take again a lot of time, okay, to find a good mapping such that will go in some bigger dimension, and then it will again you can work there and get the pattern. So there is a function, polynomial kernel function, that will help you. What does it help is it will take the conclusion that whatever the matrix that you generate, the covariance matrix for which on which the PCA will work, that matrix is what basically calculate the similarity between two matrices that you give. So this polynomial function also will help us. You just give two different matrices, it will give you the similarity between those two. Okay, basically one of the, like in some different basis, like in some different basis, right? Some different dimension. Okay, so there is a function, like I told you, the function was 1 plus x transpose, or you can take any constant function that doesn't make any change in, right? So polynomial is of like 1 plus x of x transpose times p. Okay, so that p can vary. So if you want to go to like seriously very high dimension, that the value, the p will tells you, like for example the number of dimension on which you want to change, like you want to go, let's for example from there was like you were working on some two dimensional data set itself, and then you want to go to, you want to change it, like you want to go to some seriously very high dimension, like, and then there you want to check the value. Because now if you have this type of a function, now it becomes very simple, right? You just have to give the value, it will calculate for you, right? You can just vary the number of p also. Okay, and then it will go to some different like very high dimension. You can work the PCA there, and then it will help you to reduce the dimension, even find the pattern also there in the very high dimension. So what you can do is see if the value of the p, so if the dimension is d for this case, then the dimension for xi belongs to some d dimension. Now if you want to go to some bigger dimension, so basically if we have the polynomial of the degree p, so it will, like the formula is simply this will go to directly to p plus d choose d dimension, this dimension it will go. Okay, so for us we were just working on some d equals to 2, and then we took the help of some polynomial kernel function for degree 2. So it was, for us it was going to some 6 dimension and with some mapping, and that we got an idea also which mapping it was doing. So this mapping it was doing. Is it clear till now to everyone?
Sir, one doubt here.
Yeah, go ahead.
So in this second bit where we are trying to actually go from D2 to D6
Huh?
into higher dimension, but usually goal of PCA is to reduce the dimensionality, right?
Yeah.
So when we go from D2 to D6, will that be then again problem or is that okay?
That's the issue again. So, but see, we went from 2-dimensional to 6-dimensional, correct? Right? But we already know
Yes,
something, right? Just now we have concluded something, right? In the starting, what was the first issue that we were having? If your dimension is very high, how do you work? You just start going work with X transpose X, right? If you'll work with X transpose X, maybe the number of dimension will decrease, right? Because it will be in the n cross n. See, what was the first issue with us? The first issue was if you have a very high dimension, you'll work with X transpose X, and then from there, whatever the eigenvector that you are calculating, so you'll take the help of X transpose X and come upon the conclusion to calculate the eigenvector corresponding to X transpose. What did we get? X times, like, what did we get? That beta, whatever the value was there, X times that V, X V upon root of n lambda, right? This is what we got. This was the first issue, right, where the dimension was very high, so we came
yes,
upon
sir.
some
Yes, sir.
conclusion, correct? So now in the next problem, in our this problem, the next problem where the data is not linear, so what we have tried to do is we just went to some bigger dimension, higher dimension. We came from 2 to 6, right? And in that 6 dimension, what we'll do is again we'll use this method. What we'll do is, so whatever the transform matrix, so
Understood, sir. Understood. Thank you.
we'll work with this phi of
Mm.
5x. So now phi x transpose phi x will work with this, and then we'll try to calculate the covariance, the eigenvector corresponding to 1 upon n phi of phi x transpose, something like that we'll try to do, and we'll see that what we are going to do. Is it clear to
Okay, sir.
everyone?
Yes, sir. So, sir, idea here is to go to higher dimension to find some pattern, right? So,
Correct.
okay, sir. Thank you.
So the
Sir,
basic idea is what only, like, the basic idea is to go to higher dimension and find the pattern. Yeah.
sir,
Go
we
ahead.
have to select P ourselves. Try different P's.
Yeah, you have to try. Yeah, totally. Yeah, you have to try be different, like from our side, like your side itself, and then because you don't know na, in which dimension and where it will be finding some, it will be lying on some nice flat pattern, right? So you'll have to try some different p. Okay, because here it depends on p, it will go to some different dimension, right? It all depends on p only, right? Because you can see that formula p plus d right? So the dimension of the vector is constant, that is fixed. When you will change the p, it will go to some different dimension. Okay, and in that different dimension, your what this polynomial function is giving you, what, the dot product of something. That dot product is what, the k of ijth element, right, of your data matrix, the transform data matrix, correct? And that will, from there you'll work on the PCA. I hope this is making some sense.
Yes, sir.
Correct. Yeah, so I'll just try to write everything. So what we have to do is, from starting we have so now we have the polynomial kernel function also, right? So what we will do is, we are just going from some d to some bigger d, and this d is much larger. D will be much larger as compared to d, because we can see that whenever the p was equals to 2 itself, and then the d was 2, it went to some it went to what, 6 dimension, right? If you'll just increase p to some 100 or something, it will be if you'll just increase the p value to 100, what will be the value you'll be getting? Some 100 2c 100 or 2, right? That will be very high, right? That dimension will be very high. That will go to that many dimension, correct? 100 times 100, something like that. So 10 of 1000 dimension. Is this clear to everyone? How we are going to some bigger dimension?
Yeah, it's okay.
Yeah. So now after finding some the kernel function, like because it gives us the dot product and we need the dot product only, right? So now the method for us is like, and how does this whole algorithm will work, that I'll try to say, like, that how will this kernel principal component analysis, if we are going to some bigger dimension, how will that work there. So that we'll try to see. So now the first step would be, now we have that polynomial kernel function. So we can change the value of the p. We'll go in some bigger dimension, whatever the dimension that you want. Okay, and there it will help you because the k of ij will help you to calculate 1 plus xi xz transpose of p. That will help you to calculate basically the data matrix, the transform data matrix. It will help you to calculate the transform data matrix. Correct?
Sir, how this P is decided?
Yeah, p it's like totally hit and trial. You have to randomly give the value of a p because you don't know na, from in which dimension it will be. You'll be getting some good.
Okay, some shapes.
Yeah, correct. So that you don't know. So this again can be like with the help of the elbow method only you can calculate the value of the p also. Like you will transform p in some bigger dimension and then you'll apply the p share, right? If with the help of some, let's for example from in that dimension you'll try to come upon from that d dimension. Let's for example you went from d to some bigger d, okay, and then from here you want to calculate 5 PCA or maybe 3 PCA. With the help of this 3 PCA, if you are able to extract most of the information, then you can see that in whatever the p value that you have fixed, that was good. Correct. If you have, so randomly you'll just increase the value of the p from some values, right? And then after going to that dimension, you'll apply your PCA, standard PCA, and then in standard PCA you'll see, like, let's for example you'll just fix the value like I just need 3 PCA or 4 PCA, and with that 3 or 4 PCA you'll be calculating your variance, right? You'll be calculating how much information with that 4 principal component. If I'm going from some d to capital D and then from capital D to 4 dimension, okay, if I'm just fixing 4 dimension or 3 dimension, whatever the number that you want to fix, okay, what how much information I'm losing, that will help us to get the idea about the p also, right? Which p is the best one. Are you getting me?
Yes, sir. Yes, sir. Thank you.
Yeah. Okay, so what I was saying, yeah, and then so this is our okay, so this is our polynomial kernel. So we'll have to calculate the, we'll have to fix the polynomial like kernel. We have to fix the p value also. So like that you can change, like while doing the programming session we'll try to do that, right? We'll try to change the value of the p and then we'll try to see how does and how do we calculate the one of the best the value of the key if you are using the polynomial kernel matrix or the polynomial kernel function on any data matrix, right? So you have just fixed, the first step would be you just fix the value of the kernel, like polynomial function you have fixed, right? And then the second step, what you'll do is, what will you do the second step?
Calculate the values.
Calculate the value of the kernel matrix, correct?
Yes, sir.
Because you have now you have the function, right? You'll just put the value of xi, two different values, you'll be able to calculate the whole matrix itself, correct? Because kij is what, right? This is kij, right? So you'll be able to calculate all the values. If you're able to calculate the value, and that is what, this is what the kith is what, phi of,
5x and 5 transpose 5.
correct? Because if you are just writing in the form of the matrices, a ith jth value will be giving you the similarity between phi of ith and jth, correct?
Yes, sir.
Now see, and I already know about something, like we have already dealt with x of x transpose, where if I'm having the eigenpair as lambda times v, then I'll be having x of x transpose, some we have dealt with, no, so we have dealt with that x transpose x, then we can calculate the value as what we dealt with, right? W was something, some combination of x transpose v upon root of n lambda, correct? If we are taking n lambda, so this we already know. So we are, what we are changing here, we are just changing all the data set, whatever the data set that we are having, we are just changing into some transformed value now, right? If I am having xi, now I am having phi of xi. This is what I am changing now, correct? So I was having something earlier. Now I have transformed. So maybe the data set was two-dimensional, f1 and f2 earlier. Now it has changed to some d-dimensional, right? Maybe it was like now it has become f1 square, f2 square or something, f1, f2. Now it has came to some d-dimensional. But this will be, if this was the xi, this will become my xi, right? Phi of xi, the transformed value, correct?
Yes, sir.
Correct? Yeah. So now what I have to do is, because yeah, so I have got this the values, everything we have got the matrix, basically the transform matrix we have got. Now if I have to calculate, because I have that for the transformed matrix, like whatever the matrix that I was having, the same, if we will apply the same concept here also, the same concept as of like this, because here also for phi transpose, I told you, right, you just have to replace xi with phi of xi, because here we just went from some d to capital D dimension, and this becomes some transformed value, right? So if, let's for example, I just think of, because I have the matrix, right? Now I have the kij, because corresponding to this polynomial function, I have that matrix, and corresponding to that matrix, if I have the eigen values in the form of n lambda and v. Okay, so now the same, now our matrix will be what? If I have k of ij of xi and xj, I was having phi transpose xi transpose. This is now. Now this matrix I can write it. The whole k matrix I can write it. How can I write this whole matrix? What will be the value? Can somebody tell me what will be the value? The first value will be what? What will be the second value? Similarly, the all value you can write it, right?
So in the kernel function,
What?
in the kernel function that we used above, the polynomial kernel, why are
Yeah.
we like, does it matter if we use xi transpose xj or xi xj transpose?
Where? Can you tell me?
Uh, in this
Okay.
kernel,
Huh.
here, we've used 1 plus xi transpose, no?
Correct. Huh. Xj transpose. Correct.
If we used x transpose xj, then
No problem. Yeah, you can use. Yeah, anything you can use. There won't be any issue. Because see, at the end of the day, you are getting what, some scalar value, right? So the scalar, whatever you do, x transpose x or xi transpose, so you'll be getting some scalar value only, right? This is corresponding to one value, right? X ith j, you are calculating the similarity between x ith jth, like ith vector and the jth vector, correct? So even though you calculate the similarity between jth or I, it will be same, right? Because this, whatever the matrix that you will be getting will be a symmetric matrix. You already know that, right? That the matrix that you go like get is like x transpose or x transpose x. The matrix that you get is what? Symmetric matrix. So here also you are just changing x transpose to phi x. You are just doing the mapping, right? You're going to some different dimension, but the values that you'll be getting will be in the form of some symmetric value, right? So matrix that you'll be getting will be symmetric only. Are you getting me?
yes, sir. Yes.
Yeah. So that will be a symmetric matrix. So you don't have to worry. So the value that you'll be getting will be same. Okay. So we got Kij, and that was what? Phi of x transpose phi of x. Okay. If you just check this, can somebody tell me the dimension of k of this capital Kij? What will be the dimension of this? What will be the dimension of this k, capital K?
N cross N.
Capital D cross D.
See, if you are just writing phi of this capital X, what will be the dimension of this phi? So phi is what? Phi X is what? I told you this is like a data matrix, right? So data matrix, our X was in the, so here the dimension only got changed, right? So this got in the form of what? The dimension becomes what? Capital D, and the data set will be what? N only, right? So D cross N. See, when we were changing, we were applying something, we were having xi, xi, xn. We are applying some mapping we have done, right? So we have done some mapping. So after that, whatever the matrix that we were getting, what will be the, we don't know the mapping, but at least the shape we can say, right? The we have changed to some, here it was, let's for example f1 to fd, here it will be from f1 to f of capital D, but the number of the matrices will be same, right? From each of the data point we'll be doing the mapping, so the dimension will be what? N only, right? Correct?
Yeah.
So now the dimension will be D cross N, correct? For this matrix. If I was asking about the K matrix, K is what? Phi of X transpose phi of capital X. So there is a difference. So phi, whenever I am writing capital X, that's a, like the whole data matrix. So there is a difference. There was a difference. If I am writing X, that is like the whole data matrix. If I am writing only X1, that is one column vector. Correct? So if I am writing the whole K matrix, the whole K matrix is what? The whole K matrix will be in the form of, this was D cross N. This is ND. So your whole matrix will be in the form of N cross N, and that should have been came, right? Because what I was saying in the starting, I told you, right? So if I am going from some smaller dimension D to capital dimension D, that is very big dimension, right? So we are going from small to very big dimension, correct? And this was what we, I told you, this was coming from what? This was coming from some kernel PCA, some kernel polynomial kernel you were using, and that polynomial kernel was what? It was giving me this form, right? Something like this, right? The dot product, it was giving me the dot product, right? This, the matrix that we were getting was giving me the dot product of something like this phi, the mapped version, correct? So this should have came N cross N only, right? Not the D cross D. Okay, so where is the confusion where you are not able to understand? Can you tell me? I'll just go from there. Can you tell me?
So basically, after the mapping, n still remains the same, na? So that is why kernel is n cross n.
What?
After the mapping, n still remains the same. So is that why kernel is still n cross n?
Yeah, see, the number of the data point will be same.
Yeah.
See, so only the feature, like the number of features is getting increased, right? The dimension is getting increased.
Huh.
Correct? See, if you have for any data point, so in the starting I was telling you there was a data point which is in the form of a circle, right? It was f1 f2, but what we have done is, so, see, in this case, let's for example I took from f1 square and f2 square, maybe the dimension here is same, so it's fine, but let's for example I took one more feature f1 f2 also, so now the dimension is 3, correct? But the data point corresponds, so what, let's for example this was a data point, the value was, let's for example 1 and 2. Okay, so this whatever the data point, so for each of the, so for this data point xi, the fi is 1, f1 is something, right? For this data point x1, the feature f1 is 1 and f2 is 2, correct? So now my transform data point after mapping, this value will become 1, this will become 4, and this will become 1 into 2 in the new transform, the transform data point. So this will become what? Phi of xi. Similarly, you can do for, let's for example, if you are having only 2 data points in the starting, so now you will do the transformation, correct? So you will be getting, so this is what? Phi of x2. Are you getting me?
Yes, sir.
Yeah. So so here what we have done is we just went to some different dimension with the help of some polynomial kernel like PCA, or you can take the help of the Gaussian kernel also. But Gaussian will go to the infinite like dimension. Okay, and from infinite dimension you will use the standard PCA. But here in the kernel PCA, I'll just explain it again. So we just fixed some PCA. So we just fixed some kernel. Okay, maybe it can be from the polynomial that we have used, polynomial function that we have used. Okay, and from that polynomial function, because we were knowing that it is coming out to be some dot product, like the combination of some dot product, so we just took the help of that. And then what we have done, we have calculated that data matrix. The capital data matrix we can calculate, right? The capital data matrix is what I told you, right? So if we are just doing this f transpose of x1, okay, similarly here it will be phi of x trans 2 phi x1. Similarly, you can just write it, right? This is what you will be getting as a the transform data matrix.
Sir, in this matrix, each element is calculated by that x1I,
Yeah, correct.
that formula. Na?
Yeah. But yeah, from that formula itself, xi xj transpose whole square. From here you are calculating the value, each of the values.
Okay. Okay, sir.
But the value, see, correct. So from here we were calculating, but we already know that this was equals to what? This was equals to this also, right? Correct.
Yes, sir. Yes.
Yeah. So as this was equal to, so because this was, and that's why we are taking like directly, because from each of the data point we can't do the mapping. So that's why we took the help of this, the concept, the dot product wala concept. We took the help of that dot product concept. Okay, and then we were finding some polynomial. We were finding some function that will help us to get the dot product result. We apply two values and it will help us to give us the similarity between those two functions. And then this we got the data matrix. Okay, and the end. So, but again, we got stuck with the same problem. Like we are going from some D to D dimension. Again, D is very large. So whatever the problem in the starting we were having, again we stuck with the same problem. And then we will solve with the same issue. Like in the starting, we were taking the help of X transpose. Here also, we have the matrix in the form of phi of X transpose phi of X. Correct? And we have to calculate the covariance matrix corresponding to what? Phi of X transpose, something like that, right?
Yes, sir.
Correct. Yeah. So if you have to calculate the eigenvector or the eigenvalues corresponding to phi of x into phi of x transpose, right? And we already know something, we got it from the starting itself. We have to, if the eigenpair is something lambda times b, so for x transpose there will become, if it is n lambda, then it will be what, n lambda times x times v upon root of n lambda. Correct. This is what we will be getting for XX transpose that we have dealt with in the starting, right? If we have, this is in the form of D cross D and this is in the form of N cross N, because we took the help of D cross D matrix to calculate the eigenvector corresponding to N cross N matrix, right?
Yes, sir.
Yeah. So, but see what happens in the end. Yeah.
So,
So
so
for
basically, those both problems have same solution, sir.
yeah, correct. So see, the first problem, the solution was like we took the help of the smaller matrix. The second problem, there was an issue of like the data set was not in some flat line or some good subspace like linear subspace. So what we have done is we went to the higher dimension. But when we went to the higher dimension, we used the same concept that we have used for the first issue.
Yeah, exactly.
Correct. So but here we'll stuck with some other problem also. So in the starting one, the starting problem, because we have to calculate the eigenvector corresponding to x transpose, we took the help of directly, because v was the eigenvector corresponding to x transpose x, so directly we took the help of x times v of root of n lambda. But here what happens, because this x is what, earlier we were having the data set, right? Now we don't have that. Now we don't have, right? We just have the dot product wala data matrix, correct? We don't have that exact data matrix, because we were not aware of the we see now whatever the data set that we have done some transformation, but that transformation we don't know, right? Because with transformation we don't know. If we were knowing the transformation, why like we will use the polynomial kernel function? We were using the polynomial kernel function just to that, because there was a catch. There was a catch that the matrix that we are calculating, the covariance matrix, okay, that was in the form of some dot product catching the similarity. So that's why we use the concept of polynomial kernel function directly get the transform data point, not the transform data point, like the covariance matrix corresponding to the transform data point. Are you getting me or not?
Yes, sir.
Yeah, see what happens is, see this is a bit complex to understand, like I can understand that. See what happens is, like whatever the you were applying some mapping, but the mapping you were not knowing, right? So that's why you took the help of this, the dot product concept, that is similar, calculate the similarity between two vectors. That was coming out from where? Polynomial kernel function, right? We took the help of the polynomial kernel function to calculate this, correct?
Yes, sir.
Right? So but we don't have the exact mapping. Do we have this? We don't have this, right? This we don't have, correct?
Yes, sir.
Right? So and if we don't have this exact transformed matrix, if you don't exact transform vectors we don't have, then how will we calculate? So at the end, whenever, see we were having some matrix, yeah, so this, because and this was the eigenvector corresponding to x transpose, right? And this is what we need, but for this matrix we don't have this x, because we have what? Phi of x times whatever the eigenvector corresponding to upon root of n lambda. But with this we don't have. Do we have this? No, right? Phi of x we don't have, correct?
Yes, sir. In some cases we can know this function, but
Which this function is like, see this function we are not calculating at all. This is the mapping, right?
yes,
We are calculating what? We are calculating the data, transform data, like the covariance matrix, like this we are calculating, right? Phi of this we are calculating, right? This we are getting from the polynomial kernel function, correct?
yes, sir.
So because we don't have this, so if we don't have this, how will we be able to calculate the eigenvector corresponding to our the like this matrix, the covariance matrix corresponding to the transform? This, how can we calculate the covariance matrix corresponding to this? We can't, right? Can we?
So actually we want to calculate the phi of x.
No. See, see to solve. See, if I'm coming from, if you are going from some d dimension to the d dimension where you are able to, so here the data set was non-linear. Here let's, for example, the data set that you have got is linear. So after that you have to apply some PCA, right, to know the pattern, correct? If you have came to
Yes,
some d dimension, bigger c dimension, you have to apply some PCA, right, to go to know about, if you have to know the pattern, correct? To know the pattern, if you have to apply the PCA, what do you need? The best PC, like the principal component, the best direction where the variance is maximum.
yes, sir.
Correct. Yeah. So if you need that, so you have some matrix, right? So you have applied some d, here it was x, but here after transforming you have some this one, this man. But exactly the mapping you don't have. You just have the K matrix, right? K matrix consists of what? Phi x transpose phi. This you have. You don't have the exact mapping. You just have the dot product. And dot product, how do you get the dot product? From the polynomial kernel function.
Got it, sir.
Got it, right? So you have this function, but you have this this function, this matrix you have. But exactly in the end, what do you need? If you have to calculate the PCA, you need the eigenvector corresponding to this function, right? X transpose, not X transpose X. But you have what? X transpose X, right? But we know some properties. From X transpose X, we can come up to XX transpose X. We can come up to XX transpose, right? Here, if the eigenpair is lambda times V, we'll be having n lambda times V, we'll be having n lambda times what? XV upon root of n lambda. Correct? This is what we have started in the starting we have read, right?
Yes, sir.
Correct. So now if let's for example for this matrix where this k matrix that we have got from the polynomial function, polynomial kernel function, for this matrix, if you have the eigenvector in the form of some beta or something, let's for example you're having beta as the eigenvector corresponding to your the transform matrix that you have got from the polynomial function. But for this, for the need of what is the need, like we need the eigenvector corresponding to this matrix phi of x transpose. This is our original, the covariance matrix, correct?
Yes, sir.
So what will be the value? So eigenvector corresponding to this matrix would be x times, like not x times, because we have phi here, 5 times x multiplication with what? Whatever the vector that we were having, v times under root of n lambda. So the same thing, right? Here also, here only the one thing was there. Here x times v upon under root of n lambda. Here we have v times, like in spite of x, we have phi x.
Yes, sir. So we want to know the data points on the higher dimension.
Yeah, so we have to apply the principal component analysis, right, on the bigger dimension, right? So for
Yes.
applying principal component, what do you need? The main principal component.
Yeah, the data in which we have applied it, the phi of x, basically.
No. See, if you have to apply, if you have to get this, these are the eigenvectors, right?
Yes, yes.
Eigenvector. To calculate the eigenvector, you need this mapping, right? But we don't have this mapping. We were
We do.
always from the start, correct?
Yes,
So
yes.
that's why for this type of a problem, we'll not be able to calculate the eigenvector. But one thing we will be able to calculate. If we have to calculate this, see, W equals to what? W equals to phi of x transpose, whatever the, if let's for example beta was the eigenvector corresponding to the this matrix, phi of x transpose phi of x. So we'll be left with n lambda. So this would be the value,
Yes.
correct? But what will happen? See, because we don't have this phi of x, this mapping we don't have. But one thing we can do, see, when we were applying the PCA, what we were storing, I told you something, right? If we are applying some PCA, PC1, if you are just storing PC3, 3, so for each data point, what you were storing? You were storing what? Scalar projection, right? X1 transpose PC1, X2 transpose PC2, X3 transpose PC3, correct? This is what you were storing.
Yes,
This is
sir.
what you were storing, right? In the end, you were storing this only. In the end, you were just leaving everything. You're just storing this, because now you have just from n dimensional you came to some 3 features, and you were storing the scalar projection of each vector in principal component PC1, 2, 3. So here also, what we'll try to do is, because we are not able to find the principal component, we'll try to store the projection. And see, let's try to store the projection. What will be the projection? Projection would be what? If we have x vector, and if you have to calculate the projection, x transpose W is the projection, right? So for
Yes.
this matrices, if you have to store the the projection will be what? Phi of xi transpose wi. This would be the if we have this as an eigenvector, because we are not able to calculate, we just want that at least we should at least store the scalar projection of each of the vector, each of the the mapped version into the eigenvector, because we are not able to calculate the eigenvector. Why we were not able to calculate? Because this mapping we were not having. Are you able to understand this or not?
Yes, sir.
Yeah. So what we'll do is we'll just try to store the scalar projection of each of the mapped version of the data set onto the eigenvectors. Correct? And what is this value? If we'll just x transpose of this value is what?
Sir,
Yeah.
sir, as you said, we do not have this mapping. That's why we are
Huh.
not able to get eigenvector, and that's why we are trying to compute a scalar projection, right?
Correct.
But
Correct.
now we still have this phi x transpose, but we do not. But then how do we get mapping here?
See,
Because this
that's
phi we did not have earlier, right?
correct. Correct. See, what is the value of wi? That's a good question. So, if what is the value of wi? Wi we know, right? What is the value of wi?
Yes, sir, we know this wi, but we don't know this first part.
Okay, we'll write. See, we'll try to write that. Wi is what? Wi is 5 times
Right.
x of vi upon root of n lambda. Correct? Correct?
Okay, again, this is
Hmm?
can be calculated from the same formula.
What? Which formula?
And that you used xi xj plus 1 whole power p.
No. Whole power. No. Yeah, correct. This value can be calculated. Now we can calculate this value or not.
Yes,
This
sir.
is what? This is the dot product, right, of each of the vectors.
Yes, sir. Yes, sir.
Correct. So see, we were not able to calculate the w, like the eigenvector. We were not able to calculate because we don't have the mapping. We don't have the mapping because it was very difficult to map each of the data into some n dimension. But we took the help of the polynomial kernel function. Polynomial kernel function helped us to directly transform the smaller data to some bigger dimensions. Correct. And from that bigger dimension, when we went to some bigger dimension, we try to use the standard PCA to come again to the smaller dimensions where we can find some pattern in that dimension, in that values, in that mapped values. Correct. But that kernel function, function that we used, that what it helped us? It helped us to calculate that data matrix, the transformed data matrix. We were not able to get the direct mapped values, but we were able to get the kernel, this function, right, k function, where it was in the form of phi transpose x into phi x, because it was the form of some dot product, right? So now after getting this matrix, now as we all know that the if you have to apply some kernel, if you have to apply the PCA, what do? You just need that best eigenvectors where the variance is maximum, right? But you need for not this matrix, you need for x of x transpose, that means phi of phi x transpose, you need for this matrix. Correct. So we know already some similarity between those two, are almost like similar type of a symmetric matrix, like, and we know some of the properties of x transpose and x transpose x that we have derived in the starting. So we have the eigenvector corresponding to this. So we were having some eigenvector like beta k or something, you can write it. I did not represent, I just telling you the concept behind that. So now, and if you have to calculate the eigenvector corresponding to our exact covariance matrix, because that is what we need. And if we have to calculate the like eigenvector corresponding to the exact matrix, this is what we will be getting. That we are getting from our starting, like x transpose x and x transpose. From here we are getting, right? But now we know that this mapping we don't have. If we don't have the mapping, we can't get the eigenvectors. So now we just compare. So in the back of the mind, we should be having that normal PCA. So normal PCA, what we were storing? So we were storing this the scalar projection, right? A scalar projection we were storing for each data point. If you have changed the data point, this was the data point. If you have changed PC1, this is the PC1 and this is the PC2. So you are just calculating the projection and you were storing that. So here also we thought, okay, if I am not able to calculate the eigenvector, let's calculate the scalar projection, that store that only, because that is the need. Like that is what we store in the end, and we worked on that. Correct. So what we have done is we try to store the scalar projection, and when we store the scalar projection, that becomes what? X of phi x I transpose w k. Okay, and when then we write the value of this w, that is the eigenvector, and that is what phi of x or times vi. Vi is what eigenvector corresponding to what your what vi is what eigen can okay let's so this, can somebody tell me the shape of this the whole, if you have, can tell me the shape of this directly. You can say I am telling you, right, this is what the scalar projection, right? If you are just doing the projection of like what you are doing, what you are trying to do, you are just trying to store some
N
scalar
cross N.
projection, so that will be
N
1 cross
cross.
1 only. What
Sir, for the right hand side, it should be N cross N.
which okay, let's write it again, let's try to write it. That will be what phi of xi transpose. I want to store scalar projection of the first mapped vector, okay, onto phi of b1 upon root of n lambda 1. What is the dimension of this? There will be 1 cross d, correct? This is right. This is what this is the scaled like the mapped. If you are trying xi, this will, from d dimension it went to some rd dimension, right? And if you are taking the transaction the transform, it will be 1 cross d, correct? What is the dimension of this matrix?
D cross 1.
So it
This is
was N
d cross
cross D,
n, right?
right?
This is d cross n, right?
Yes, yes.
Correct. And what is the dimension
Sir,
of this vi? Yeah, go ahead.
sir, for the first one, it should be N cross D, na? Phi of X transpose.
No, this projection that we are making, this projection that we are making is for one vector, the first one.
Okay, it's
Because
one.
see, when yeah, so what we were doing in the principal component, we were having PC1 and PC2. So for each vector, we were taking the dot product and we were storing some scalar projection, right? So let's, for example, for this phi x1, I'm taking this. I want to calculate this value. I want to calculate this value is what the projection of phi x1 on PC1, correct? This is what I want to calculate. So this phi x1 is the first vector in the mapped version. And then what is this? This is what? This phi x1. See, and phi, if you are getting confused in here, if you are getting confused here, why, how can I, this is what? This is WK, right? This WK was what? For our normal x transpose, how generally we write? X times V upon root of n lambda. X was what? X was what? The data matrix, right? For this matrix, what will be the this will be phi of x. This will be, what will be the dimension of this phi of x? Capital D cross n, right? Are you
Yes,
not
sir. Yes,
getting
sir.
this?
Yeah, Phi cross
Yes,
is.
Yeah, and what will be the dimension of V1? V1 is what? The eigenvector corresponding to what? Your this matrix, right? You just think of that this matrix. Then V1 will be what?
N cross 1.
N cross 1. So you are left with what? D1, so 1 cross 1. And this was expected, right? Because what we are calculating? We are calculating the scalar projection of this phi x1 on principal component first. Or you can say that WK, the kth principal component, we are projecting. That should have been came as scalar only, right? Did you understood or not? So and see, so what happens is, so we want to just store the values. So similarly we can store the values for each of the wk. We don't have the wk, like the exact value we don't have eigenvector, but we are able to calculate, store the scalar projection of all those data set, all those mapped value, right? With this, right, with the help of this formula. We don't have the exact W eigenvector, we were not able to, because we were not having the mapping, but we were able to calculate the scaled version of that projection, right?
So, but how we will calculate this phi of x1 transpose phi of capital X? How we multiply these two?
Yeah, see, come, I'll tell you. So this we have what? Let's do it for one example. Take one example. So I have to calculate this value itself, the first one. So this is phi of xi and this is the wkth projection. So what will be the value? Phi of xi x1 transpose phi of capital X, because this is coming from the W. This is wk. The wk we already know the formula, wk times b1 upon under root of n lambda. Okay. So
Yes.
now what will I write? How can I write this phi of x? This will be what? Phi of xi, correct? Transpose. If I have to write this matrix is what? Phi of x1, phi of x2, phi of xn, right?
Okay, okay, okay.
Can
So,
can I write it like this?
yes, yes, yes. Okay.
Right? And if you will multiply this matrix, you will be coming up with something, right? It will be what? It will be phi of x1 transpose phi of
Excellent.
x1
Mm.
plus, right?
Got it, sir. Okay.
Times v1 upon n of lambda 1, root of n lambda.
Mm.
If
And
we'll
now,
just try to write it, yeah, this is basically k1 only,
yeah.
the first row of the kernel matrix.
Okay. Now this one we can calculate using that one plus xi transpose whole power p formula.
Yeah, that you can calculate from there also. Yeah, this is the first row of your kernel matrix that you are having. The first row. This is what the first row of your kernel matrix itself.
Okay, sir. Got it. Got it.
This is not plus. It will be. So this is like the first row or of the column matrix itself. I hope this somewhat made sense. Are you able to get in like
So
this
there's
is a bit, yeah.
still a little bit confusion. Like after we get the kernel matrix,
Hmm.
what are we projecting on?
After getting the kernel matrix,
Yeah,
what are
then
we Hmm.
where do
See,
we project?
okay, I'll just compare both, right? So this is the normal PC that we were doing, standard PC, right? So in the standard PC, we get, let's for example, PC1 and PC2. Okay. So if we have got PC1 and PC2, for each data point, you were storing some scalar value, right? If this is x1, so we were just projecting this x1. So this is x1 transpose PC1, right? We were doing similarly x1 transpose PC2. This in this form we were storing the data, correct? Are you there? Yeah.
Yes, sir.
Okay. Similarly, for now, for our case, now for the kernel matrix, now you have the kernel matrix, correct? It is in the form of some dot product, right? But that is in the form of a dot product. That's fine. And we already know that we are not able to calculate the eigenvector corresponding to our matrix. We are not able to calculate of this because of this value. Because of this value, because mapping we were not having. If we don't have the mapping, what we have tried to thought of, we thought of, okay, let's for example, we were having some k eigenvalue eigenvectors, we were having some k eigenvector. I don't know what eigenvector it is, the exact eigenvector I don't know, but can I store the data, like can I store the scalar projection? This is what I thought of, because in the end, in the normal PC also, what in the end what we need, this is what we need, right? This matrix we were counting, right? This matrix was what? The upgraded, the transform matrix. This is our transform matrix, right? So see, with the, if you have a, if you are applying, this was your data set, you are just what, this is our representative PC1, okay, and this is our data set, correct? This is the one representative and the one coefficient. This is what the coefficient with the principal component, right? And in the end, what you were storing? You were storing some scalar projection, right? And what is that scalar projection? That scalar projection we were able to calculate for the kernel matrix. Have you understood anything or no?
Yes, sir.
What is the doubt? Like, can you tell me specifically what's the doubt?
Sir, how long are we going to continue, sir?
Yeah, that's like the done only. Like,
Okay, sir.
Sir, I actually understood, but it's like visualizing is bit difficult, and that's
yeah, yeah.
why.
When we'll do the programming session, maybe tomorrow we'll try to visualize. So it will help after that. At least the basic idea you got it right. I'll just recap all the
Yes,
things. So
theoretically, yes, I think mostly everybody is able to understand. But when it comes to like formula and these notation,
Yeah,
so
notation and all I didn't even bothered about. Yeah, that I can say that notation I didn't bothered about the notation because I just try to say the idea about that. Like maybe when we'll deal with some of the problems. So day after tomorrow we'll come up with some problem. We'll try to solve those questions. Tomorrow we'll be having the programming. Maybe we'll try to visualize those things. We'll try to go to some different dimension and then try to visualize how does it happen. Will with the help of the polynomial kernel PCA. Okay.
Sir, please summarize once with
Yeah, yeah.
a bit slow pace, sir.
Okay, okay. So what happens is, see, we have done the PCA. Okay, in the PCA, what happens? We were trying to reduce the dimension. Okay, but while reducing the dimension, what we have done? Let's for example, we came upon 4 dimension to 2 dimension. If we are coming from some 4 dimension to 2 dimension, so earlier my data set was something like that: xi, xn, the dimension f1, f2, f3, f4. Now it has changed to 2 dimension. Let's for example, this is v1 and v2. This is my principal component first, and this is second. This is xi, x2. So now what I am storing, like I'm not storing this data point. Now I'm changed from 4 dimension to 2 dimension. What I am storing is x1 transpose v1 and x1 transpose v2. I am storing x2 transpose v1 and x2 transpose v2 I'm storing. So this is the data set that I'm storing, and I'm working on this data set now, because now from 4 dimensional to 2 dimensional I came, and now I'm working on this. Now I'm trying to find like I'm doing everything on this data set, right? So at the end of the day, this data set is most important, right? The scale, like the scalar projection, correct? So this is how the normal PCI did. Now what happens in PCA? Sometimes there is an issue. The first issue was for we came up with first issue. The first issue was what the the dimension the covariance matrix that we were calculating, that was in the form of x of x transpose. I'm not writing 1 upon n anywhere. That is fine. You can just understand that x upon x transpose I'm writing, and this in the form of d cross d. So, but I was having a data set where d is very large compared to n. Okay, so what I try to do is I know some of the linear algebra. So what I thought of, okay, can I do for x transpose x? If I have the x, if I do for x transpose x, because here for x transpose x I am getting n cross n matrix, because and that is much lesser than the d cross d. So what I thought is there is some similarity between x transpose x and x transpose. So I took the help of that. So I what I try to do is for x transpose x I was having the eigenvector as, let's for example, n lambda and v as the eigenvector. So what I thought of, okay, if I have the eigenvector for this case, and I know some of the linear algebra that x transpose and x transpose x both will be having the same number of whatever the rank for this matrix. If the rank of this matrix is R, so this matrix also will be having the rank of R. Similarly, the rank of the matrix X will also be the rank of R. And if the rank is R, you'll be having R non-zero eigenvector or eigenvalues. Okay. So similarly for this matrix also will be having the same case. Okay. So that concept I used. Okay, with the help of that concept I came upon one formula that if for x transpose x I'm able to calculate the eigenvalue eigenvector with much easier. Okay, so and that was what n lambda and v. So I come up, I proved also that for if the eigenvector and eigenvalue is n lambda v, so for this matrix it will be n lambda, and the only the eigenvector will change, and that eigenvector will be x transpose v upon root of n lambda. Okay, this will become the eigenvector and this will become the eigenvalues. Okay, so we dealt with this problem. Now the second problem that we dealt with, the second issue that we came upon was that if the data set is not lying on the linear subspace, what will I do? Correct. So for those cases what we have done is we just try to go from smaller dimension to some bigger dimension. Okay, and from smaller dimension with the help of some mapping. But the problem here is we can't. This is a very hit and run method. You can't know if you are going from some smaller d to capital D. Will you be able to find some like linear subspace or not there? Okay. So what we have thought of, and there was a helpful like feature also in the starting in the normal PCA when we were doing for the covariance matrix. We came upon some formula. We thought that okay, the covariance that we are calculating, that is not exactly that basically is what that is. See, if we are calculating covariance x of x transpose or x transpose x, if we are multiplying these two matrices x, or let's for example you are multiplying x transpose x, because you are working, you have to work on this x transpose x. This matrix is somewhat xi transpose x2 transpose something, and then you are multiplying this xi x2 something, right? So when you're multiplying the matrix that you are getting on which you want to calculate the eigenvector eigenvalue, you are multiplying this, you came upon one thing that this is nothing but xi transpose xi. So this is something we are getting in the form of a dot product. So what we thought of, okay, can we find some function where the final result will just give two eigenvector, sorry, two vectors, and the end will be getting something in the form of a matrix that will come upon, that will be giving me the like, see, so this is the issue. So what happens, so we in the normal PCA when we were doing, we came upon one thing. We just thought of, okay, whenever we were calculating the k value, k was something x transpose x, we came upon one idea that this is nothing but a dot product of two vectors x. If I have to calculate ij, this is basically taking xi and taking xj and calculating the dot product. Okay, so now we thought of finding one function, and we got one nice function in the form of xi xj transpose. This function, when we extrapolated, we explored this function, we came upon one idea that this is nothing but a dot product of xi and xj, but in a some different dimension. This is not, we were having some in two dimensional, but after doing this we came upon some like, if the value of p we were taking 2, now we saw that when we were applying this xi and xj two vectors here, it was going to from 2 to 6 dimension. Then it helped us, right? And this is what we were trying to find. We were trying to find some transformation that should go from some smaller dimension to some bigger dimension. Why bigger dimension? We were just trying to find something. We were trying to find what, so that it should lie on some linear subspace. Are you there?
Yes, sir.
Okay, so now what, so linear subspace, so we thought of taking help of this polynomial kernel function. Okay, and this polynomial kernel function, when, and this is what x of ij means. If you'll just put it, if you'll write it in the form of a matrix, this is k of ij. K of ijth value you can calculate directly with the help of this. And this is what helping us, this is our transforming some features small, like the data point from smaller dimensions to some bigger dimension. So if the data point earlier was f1 of fd, this is transforming from f1 to f of capital D. Okay, and transforming, but the data set that we are getting, that is in the form of x, like phi of x transpose x, because I told you, right, the function that we are using, that function doesn't give me the exact value, that gives us the value. If we are putting two vectors, it is giving us some similarity between two vectors. Okay, so we got something in the form of a matrix. Now we got something in the form of a phi of x transpose phi x. Now again we come upon one thing, that this matrix again is in the form of a d cross d, and that d is very large. So what should I do? So now we thought of, okay, in the issue 1, what we have done, we took, again it was in the form of some d cross d matrix, or maybe no, so this is not in the d cross, this is in the n cross. This is what, the phi n cross d, and this is d cross n. Correct, this is the correct dimension, right? Okay, the phi x that you will be getting is in the form of what, some bigger dimension d cross n. Correct. So now whatever the matrix that we have got in the form of this phi of x transpose phi of x, right? So this is in the form of n cross n. But we already know that if you have to calculate, because we went to some d cross d, but we went to some d cross we went to some matrix from smaller d dimension to some bigger d dimension, right? But for this matrix, what will be the exact, for which vector we have to calculate the covariance, for which covariance matrix we have to calculate the eigenvector for this matrix, right? X of phi of x transpose, correct? But we got the matrix in the form of this. But we already know that there is some good relation between these two type of matrix where x transpose x and x transpose. What is that good relation? If we are getting the eigenvector in the form of a b, here we will be getting the eigenvector in the form of what? Phi of x transpose b upon under root of n pi, n lambda. Correct? This will be about eigenvector. But the problem here is phi x we don't have. This mapping we don't have. From the starting, I'm telling you, this mapping we don't have. We have in the form of a dot product. The value is in the form of a dot product. So what will I do? And in the starting, I told you, right? What did I say? At the end of the day, what do I need? I need the scalar projection. So now we thought that I can't get the principal component. Can I get the scalar projection of those values? A scalar projection of this map value on the W. So now we thought of what? Let's try it out that. So we thought that. So let's try xi. Let's, for example, for the first data point, we tried of mapping phi of x p times root of n lambda. Okay. So now we got an idea that okay, the scalar projection I can store. So now in the end, we just store the scalar projection, right? And then with the scalar projection we can work, right? That is what we do, right? In the normal PC also we just store the scalar projection, and on that scalar projection we work. Have you got the idea? Got it,
Yeah,
Shivam?
so we're getting it, but we need to visualize it once again so we can do it together.
Yeah, it's, that will take time. Yeah, so this is a difficult portion. After that, everything is simple. Like this is the most difficult chapter that you have. Like the first 2 weeks are really difficult. After that, all the weeks are very smooth. Like from next week, it is very easy. Like clustering, mean clustering, and also those are very simple. Only this starting 2 weeks is really
So
difficult. Yeah,
this phi x1 transpose phi, this whole thing is the scalar projection.
yeah. You can see that. See, what is the dimension of this? This is what? So d cross one, right? Sorry, n one cross d, correct?
Yeah.
Correct. So if you have a phi x, that will be in the RD, right? Add of capital D, because right, this is
Yeah.
one vector, column vector you can think of. This phi x is what? This is capital X. Whenever I am writing, that is what? This is in the form of d cross d,
Hmm.
correct? This matrix is d cross d, right? And this vector is what? Vector is this V is what? Eigenvector corresponding to what? Phi x transpose phi x, right? So this again will be in the form of what? So sorry, d cross n. This is d cross n.
Yeah, it will be D cross N. Yes.
Yeah, d and n vector. So d cross n, and
And
again
this
this
will
will be in
be
the form
N
of n
cross N.
cross one.
Right. So it
Yeah,
will be N cross
n
1,
cross
so it
one.
will
Yeah,
become 1 cross 1. Okay.
yeah, because it should be, because we are just storing the scalar projection. We are just taking the projection of the one vector onto the eigenvector. Eigenvector we can't calculate, but can we store the scalar projection? And we in the end we saw that scalar projection we were able to store.
So when you say scalar projection, you just mean that like in this, we're not multiplying it again by the vector, by our eigenvector.
No, see, if you have to calculate, if you have to calculate, if you have to store, if you have a data point xi, and if you have to store pc, like the projection of xi on this pc1, how do you store xi transpose pc1, correct?
Yeah.
Correct. This is how you store.
Uh,
Okay. Now for our data set, what is the projection? This is the phi of xi transpose, like this, and phi of this is our vector, because this we have to project, like this is our matrix, this is our vector data set, right? For this data set
yeah.
we have to take the projection of phi of xi on wk. This is our eigenvector
Hmm.
we are not able to calculate because of phi x we don't have. Are
Hmm.
you there? So now
Yeah.
what we do is we just return in the form, because can, and we thought of okay, can we store the scalar projection? For the scalar projection, what, how do you write? For any vector x transpose y, correct? If you have to take the projection of x on y, you take x transpose y. correct? So we did that project X transpose of X, and what is this WK? WK we already know that this is what upon V upon root of n lambda. This we got it from where? X transpose X may, what was the value? N lambda V. So if for X transpose, what is the value? N lambda V upon root of X times n of n lambda, right? So in spite of X, you are writing phi X, correct? Times V upon root of n lambda. Are you there?
But how will we get V in this?
Okay. So if we have to calculate, yeah. So now next one. What is this matrix? What is this vector? See, phi of xi. This will be in the form of some vector, right? This will be in the form of some vector. The row vector you can think of. And how will you write phi of x? Phi of x is what? Phi of x1. See, I'll just delete all this. If I'm writing X matrix, how do you write X matrix? This is X1, this is X2, Xn, correct? Are you there?
Yes.
Yes, sir.
If you have X of data matrix, how do you write? This is X1, this is X data set, Xn data set. If I'm writing phi of X, this will be what? This will be the D dimension, but this will be what? Phi of X1, phi of X1, phi of, similarly phi of Xi, correct?
X. Yeah.
Correct?
Yes, sir.
Yes, sir.
Okay. Hmm. So now if I have to multiply this, both the matrix, how do you multiply? If you have a row matrix, this is what? A row, right? This is a data set of row, like row vector, right? Row vector, this is
Correct.
row vector, and okay. So now if you have to multiply this, phi of xi transpose phi of this bigger X times B upon root, constant, leave it the constant. Okay, constant doesn't make any sense. So so this is in the form of what? If you will just tell me the dimension 1 cross D, you write it xi transpose multiply with phi of x1, phi of xi, phi of, similarly phi of xn. If you have to multiply this to, how will you multiply? Directly you multiply like this, correct? How do you
Yeah.
multiply?
Right, sir.
Right.
Huh?
Phi xi
Row.
transpose phi x1.
Correct. So this will be how can you write this? If you have to write this, how will you write? You just multiply it. If this is 1 cross what D, and this is what D cross N. So you'll be getting what? If you are multiplying, you'll be getting what? 1 cross N some matrix you will be getting, right?
Right, sir.
Correct? So you'll be
Yeah.
getting what? Phi of x1 transpose phi of x1. Similarly, phi of xi transpose phi of xi. And this you can get it, right? This you can get from the K matrix, correct?
Correct, sir. Yeah.
Correct? So this will be what? This is K1. You can just write it as K1. K1, why K1? Because this is what? The first row of your kernel matrix. Correct?
Kernel matrix. Correct, sir.
Correct? So and then what? And V you already have. V to you already have, right? V, how do you calculate? V eigenvector corresponding to your normal matrix that you have calculated. So V you can calculate it, right? V is what? Eigenvector corresponding to what? Phi of x transpose phi x. Your kernel matrix itself.
Okay, okay. That's only what I was asking. V is the eigenvector corresponding to kernel matrix.
Yeah. So now you can calculate, right? So you can get the scalar projection of that. So you can store the scalar projection now.
Okay, thank you.
Yeah. Any other doubt that you have? Anyone?
Sir, can we say that after applying this the second issue, we
Hmm.
don't get the vector form of the PC one, but we get the
No, you will
projected
not be
form.
getting. No, PC. Yeah, you PC the principal component you will not be getting. You'll just
Okay.
be getting. You'll just
The
be getting the scalar projection of all the data point on the principal component.
okay, okay, sir.
Yeah.
Thank
Anyone has any other doubt? Anyone has any other doubt, or can we close this? If you have any doubt, you can just ask me. Can you close this, the session?
Yes, sir, we can close.
Yes, sir.
Okay.
Thank you, sir.
Does that help or
Thank you.
not?
Yes, sir,
Thank you,
very
sir.
helpful.
Yeah.
Thank you.
Thanks.